All right. Hello, everybody. Good morning, good afternoon, good evening, wherever you are in the world. Thank you so much for taking the time to join the Hard Tech Fund's Hyperloop Symposium Day 2. So in Day 1, we had teams from across the world present, and today we're going to have those top teams lead panel discussion sessions related to topics that they're completing research in. So here's kind of the schedule that's going to happen today. Once again, just want to thank you to Cooper Hyperloop, Hellman Hyperloop, Hyperloop IITB, HyperExcite, and OneLoop for taking the time to participate, to write these research papers, and to present really great presentations. You guys have all done a terrific job. Not only have you done all this work, but you've also helped each other's work and support each other's work, which is, I think, what a peer symposium is, proper peer review. And also thanks to our stakeholder organizations, ACOM, Mahek Hyperloop, and Virgin Hyperloop One, and the others who are out there who are helping to provide good reviews and to take part in this panel discussion later today. So the basic setup is there is a team in each section that was picked based on the votes that they received yesterday on the research papers and the presentations to moderate a panel today. So they're going to be asking questions and leading a discussion with regards to the topic that they're very strong in. The idea is to create this discourse between top researchers and stakeholders so that we can all work together on awesome ideas. So yeah, feel free to ask questions via the Facebook live stream or on Slack, and we'll try to make sure that it remains to be a very engaging discussion. And yes, it is recorded on Facebook Live. All right, so without further ado, again, welcome to Hyperloop IIT Bombay. They're going to start with a session on propulsion. So you're going to have an hour to begin speaking on that. Please take the floor.
Yeah. Hi, Samarth. This is Fenil Soni, the team leader of Hyperloop IITB. So along with me, we have 4 other members from Hyperloop IITB. Our team, my co-team head, Abir, subsystem head of propulsion, Shreyashree, and chief electrical engineer, Shreyashree, and chief mechanical engineer, Lalit Kumar. So we are a team of basically 50 plus members working in across 8 subsystems, propulsion and aerodynamics and stuff, including both postgraduates and undergraduate students. So we started recently around like last year only in September. And since then we have been able to get our design selected for the desert loop competition hosted by Arizona State University. And we are right now working on our design of the LIM. So Abir, you can take over. Okay, Shreyashree.
Hi. So yeah, we're currently working on designing our own LIM system, which is the biggest challenge for now when it comes to not only the LIM itself, but also working on other subsystems which are related to LIM. So yeah, there's time limits, and well, people just unmute. You can write whatever you want on the chat or on Slack or wherever. And we will first discuss some innovations, and then there's questions to be, and there's going to be a question answer session, which will be regarding research, or it will be regarding commercialization, failure systems, for failure modes, for example, etc. So, Lekha, are you available? Or do I go ahead? All right.
Okay. Yeah. Hello. Yeah. Hello. Shreyashree, am I audible?
Yes, you're audible.
Okay. So As we have been introduced already, I am Shreyashree. I am the Propulsion Subsystem Head of Hyperloop IITB, and we already presented our paper on LIM's design approach of our LIM. So basically, we started just a few months back, and the first decision that we made was to not just limit ourselves because of the research potential we might not have at the moment. So we started looking into LIM from the very beginning. So that's okay. Where do I start? Okay. So I don't want to reiterate whatever we said yesterday, but I would like to say that we are not only involved in LIMs, but we have already been working on. Hello. Am I still
You're audible.
connected? Okay.
Yeah.
Okay. Okay. So not just on LIM, we are also working on a BLDC motor setup. That was because from what we understood about LIM systems, that we learned that they work at a higher speed more efficiently, and they are not very good at the starting velocities like 0 to 10 meters per second or so. So, and also we need to have levitation so that it works better, and that's why we started using a BLDC motor to reach the speed of 10 meters per second, and from there our LIM will take over. That's the basic design idea we had. So that's why we have both BLDC motors and LIM. And but these systems are usually for vacuum tubes, right? So the Arizona desert loop competition that was mentioned earlier is the open air track, and for that we were looking into coal gas thruster systems. So we have a little bit of experience in that as well. So basically that's the overall idea of our propulsion system, apart from what we have already explained in yesterday's presentation. Shreyashree, could you give an explanation on the electrical dependencies?
So along with the propulsion system that we have, it's a two-part propulsion system. So that is a bit of a challenge when it comes to component selection, shopping, and overall electrical design. So I realized that the BLDC is much more flexible as compared to LIM when it comes to design, when it comes to data that I have to work with. So I also realized that LIM requires a lot of energy because it will be propelling the pod to very high speeds. Thus we took the decision to focus on efficiency, and we ended up using a high voltage system, which is approximately 712 volt at maximum voltage. That is when all the cells are charged. And there will be a low voltage system, which will be a DC-DC converter, and then a 12 volt, which will control the rest of the system, which will control the rest of the onboard computing, the control system, the shutdown circuits, etc. There is definitely a bunch of sensors along with the accumulator, inside the accumulator, as well as other system vitals. There is this concept of shutdown signals that I'm using, where a bunch of error signals will be classified as critical signals, and they will determine if my pod will stop or not. So if any one of those signals changes its state, it means that my pod will have to stop because the pod is in an unsafe condition. The onboard computing and communications will ensure that this information is properly echoed back to the user outside. So, of course, for the LIM, there's a LIM inverter. We don't really have the expertise to do it ourselves. I'm just an undergrad. A lot of us are undergrads. Some of us are postgrads. So we decided to have an LIM custom built for us. There's a lot of demands and dependencies. A lot of them have not been sorted out yet due to the custom LIM inverter taking some time. And so thanks to COVID, we're all stuck at home. We can't really test our systems. So we end up using tools like mathematical models and simulations. And we use tools like FMEA, which is failure modes and elements analysis. We use that so that we can analyze where our system can go wrong and how the system will respond to a certain parameter going wrong. So the next question comes, how does all of this fit with our overall goals? So overall, when it comes to personal goals, for example, why am I over here? Because I get my work experience. I get some experience on working with a system like this. I helped to contribute in this whole Hyperloop project, which is a very good thing for me when it comes to experience, and overall, I really like to do it. I think a lot of people would agree to that in my team. Overall team goals, well, we have all this computation, simulations, it just makes us better prepared to make a pod in real life, and thus there are lesser chances of technical and design errors, and just the time wastage and resource wastage that is caused due to those things. And ultimately, we want to make a good submission to the SpaceX competition and assisting in the efforts to help this whole project reach a good conclusion. So that was about the goals section as well. Lekha, anything more you want to add?
Okay, I think that's about it. We can open the floor for questions and we can proceed further, I guess.
Wilson channel chat, but I'll repeat it here. It's I was curious as to how you came up with the 700-volt battery figure.
So I was looking through the different configurations, different voltage levels I could see for motor controller system as well as the LIM system. And I realized that the cells that I was looking at when I was using a 400 volt system, the current would be really high, and that would not be that was too much current for the cells that I was looking at. And I was also facing heating issues at those currents. Hence, I decided to increase the voltage for getting slightly lesser current because the power output will be same. So I ended up increasing the voltage, getting lesser current. So cooling would be slightly less of a problem that way. So that way I can make my system overall a little more efficient because cooling is a major challenge. Currently, we're using phase change materials for that. We had definitely toyed with the idea of using a coolant fluid and a complete circulation system, but that was a weights issue that we realized. Does that answer your question?
Yes, thank you.
Okay.
I've also put a question in the Slack chat, but I'll just repeat it here. How do you plan on sourcing the components for the LIM that you've designed? Do you plan on buying a motor as standard, outsourcing the construction to a third-party company, or building your LIM in-house?
Hello?
You're audible.
Okay. So yeah, the current idea is that we will be outsourcing the manufacturing to a third party because we don't have the infrastructure to build or even test them at the moment because we are just a team that started about a year ago, and funding issues are still there, and so we are looking to outsource them, but we are not there yet to start looking into that completely because our design has to be perfect before we go for testing or prototyping even.
Of course, yeah.
So that's what we are looking into now.
Excellent. All right. Well, thank you.
Okay.
Any other question, guys?
I'll ask a question. Does your team consider the inverter system for the motor a part of propulsion, or is it more like a power or control thing?
In our team, most of the subsystems like propulsion and electrical are working very close together. It's not exactly there is a division between who works on what. We are mostly collaborating on all of these things actually. So that's how we are working on.
I like that. Good answer.
Yeah, yeah.
I mean, it kind
So
of
it's not
depends
exact.
on what the subsystems have. So first of all, propulsion has to get their stuff sorted. then electricals and some mechanicals have to get their stuff sorted. So the entire design process, it's a multi-step thing. So different subsystems will collaborate at different points. So things overlap.
I have a comment. It's about the batteries again. I was surprised to hear that you picked a battery voltage that's so high. And I was thinking about, you know, the currents flowing through the limb as well, and how they're so high, and that introduces a heating issue. But I think no matter, well, it's like Ohm's law, right? So if you have a super high battery voltage, then you have to have a higher impedance of the limb so that less current flows. And so that means having like a lot more windings. So I think that might make the manufacture of it more difficult, but would make a better system. So I guess I see why you choose to outsource.
That was the main reason why such a high voltage was chosen, because we kind of need some qualification for working at voltages like this as well.
Yeah,
we can't really use voltages like these, just like that.
Certainly, thanks.
All right. Is there any other questions regarding the rest of the subsystems or the rest of the pod or the team in general?
Yeah, I'm curious as to the spacing between, I'm not sure what you call it. I've heard people call it like the sunset, but it's essentially like, I call it the wavelength, and it's like the distance that a full phase takes up on the limb. And one of the things I was thinking about is about using a commercial inverter system, but a lot of these commercial inverters are frequency limited, and so based off of, you know, slip and torque relation, it was important that the wavelength of the limb be long enough such that at the max frequency of some of these commercial inverters, that we would reach, you know, we would still have propulsion to meet our max velocity. Did you encounter anything like that? Have you done any like simulations?
Yeah, so the thing with a lot of propulsion, a lot of commercial inverters was that they were made for static applications. So they were not really, so a lot of them were not something that you could mount on a board, which would be going at very high acceleration. They were simply not rated for that. So that was one thing that we encountered while we were looking at stuff. And not to mention the specifications were slightly less, and they would end up limiting our system. Lekha, you could probably throw more light on this.
Okay.
Lekha?
Hello? Yeah, hello?
Yes, you're audible.
Okay, so can I hear the question again? I was not completely able to understand it.
Oh, yes. It was sort of like a comment question. I was just commenting that in my own experience, I found that commercial inverters weren't quite suitable for the application because they were frequency limited to maybe around 400 hertz. And so that would essentially, at synchronous speeds, we wouldn't be able to reach our max velocity.
Yeah, that was one of our first milestones that we had to cross, because we were looking at a lot of inverters that are available commercially, and we ran into the same problem. That's why we decided to have a custom built inverter. We are not sure of the parameters yet, but that is what we have to be doing, because like you mentioned, the frequency is very low and it will not help us much in the long run, or even for making a short prototype. So we are looking into making a custom inverter. It will be in collaboration with the electrical subsystem, but so that's our idea. We are looking into making a custom inverter only. We cannot take commercial inverter and work with that. So I guess what was your approach to this problem? Were you coming to the same conclusion, or did you have another idea?
Yes. I actually have been. I'm on the power team, and so I have been sort of spearheading the research into developing our custom inverter, and as such have been working with the propulsion team. We're still not quite positive that we're going to build a custom inverter, but I tell our president and the project manager that we should, because it gives us a lot more control over our system, and I think it'll give us a better result. But I did say that we may be able to use a commercial inverter if the wavelength of the limb is long enough. But again, I think that's difficult to do because I think it decreases your starting torque because it reduces the number of poles that you can fit on your pod.
Yeah, that is one of the primary concerns that we were looking into. Yeah, so I think that answers the question. You could actually give us some pointers on where to actually look into when we start designing our inverter, I guess.
Yeah. Always happy to help a fellow, student.
Yeah, thank you.
Ryan, can I ask something? Like, I know I'm supposed to be the one who's going to be taking questions, but I'm just curious. Did you guys actually decide and plan out how to make your own custom inverter?
We're working on it. And when I say we, it's a lot me, but my team they help. About 8 months ago, I mean, I probably started working on induction motors a year ago, like just researching. Like I just found out about it a year ago and thought, hey, Hyperloop's pretty cool. So 6 months ago, I built my first prototype, which was nothing more than a glorified brushless DC motor controller.
Because for something like Hyperloop at voltages like these, which are used for a better system, the one thing that comes to my head is characterizing. So commercial inverters or whatever I buy commercially, they're very well characterized as compared to what I will be making. And I will have to look at so many different factors that it's just a lot of time. I have my academics and projects as well. So that is one of the reasons why we decided to give up on the idea of doing a completely in-house inverter.
Oh, it's certainly a lot of work.
Possible. It's just a lot of work. There's a lot of safety concerns because anything going wrong can be catastrophic. Yeah.
Yeah, I've been shocked a few times. Not any in my own home, but like, I was young. I was dumb.
You survived.
I am still here, so. But yeah, I actually just finished my prototype, the newest prototype, about a week or two ago, and I think it's going to be pretty promising. It's sort of like a little variable frequency drive you plug into the wall, and I'm hoping it'll give us a chance to figure out like control algorithms, how to optimally control the induction motor. It features a 500 megahertz microprocessor, Arduino compatible, with a field programmable gate array for gate drive waveform generation to like create sinusoidal waveforms, and a bunch of power IGBTs and power supplies and bootstrap capacitors, and sort of like a power electronic architecture for an inverter.
That's pretty good. Did you characterize all of it?
Did
you end up with a gate? Did you characterize the input voltage and the profile, the output voltage and the profile, in intermediate signals that you have, etc.?
So I ran some simulations based off of the PWM output, and the input voltage is like 120 volts AC, which is then rectified to about 170 volts DC. And then that's sort of chopped up into three-phase AC by IGBT modules.
That's pretty good. But
Thank you.
extrapolating it will be hard, but I think it will be pretty rewarding.
Yeah, I'm
Extrapolating
hopeful.
it to high voltages.
I'm hopeful. I've worked with high voltages before. In high school, I built some Tesla coils. So
That's interesting.
yeah, it's fun.
So for both of you, and also for Hyperloop UCI, like, because I know you guys were also working on linear induction motors, like what are some of the asks that you have for commercial manufacturers of limbs? Like what is something that you wish that they would do, or like, you know, how would you make it, besides obviously giving you a nice limb for free? But like, you know, how, like, ways to improve their product and kind of get it ready for your use cases.
Well, for a linear induction motor, obviously this is a very niche application and there's not a lot of commercial solutions for it yet. But for a theoretical commercial solution, I would say, well, what I'm trying to implement in my inverter, when I think would be a good solution, or maybe a good solution, is wide frequency range, because we don't really know how fast we're going to be able to go, but we know that we want to go as fast as possible. And so if that's dependent on frequency, we need to have the highest drive frequency we need. And that includes changing the modulation type of the inverter. So for low frequencies, it uses pulse width modulation to sort of approximate sinusoids in the inductor, the motor. But at higher frequencies, the impedance of the motor is too great for pulse width modulation. And so I think transferring over to square wave modulation at higher frequencies, even up to maybe a kilohertz, would allow us to continue to use our limb past what a normal induction motor might be rated for. And that's something certainly commercial inverters don't do.
Another thing that I noticed that a lot of commercial inverters, number one, our specs are probably way too much for them. Number two, a lot of them are not even dynamic rated properly. So they're not rated for going through a system, they're not rated for being fit into a system that is going at like 750 kmph top speed. And a lot of the times, the manufacturer expects us to treat the inverter, whatever they sell us, as a black box. And I actually want to open it up, probably tinker with it a bit, and that freedom is sometimes missing from what I buy. So that is something I wish the manufacturers could improve on. I mean, making the product a little more tinkerable. That, I don't know if that's a nice way to put it, but it's a good idea to be able to know the inside out of the product and a very well detailed data sheet.
I mean, that makes a lot of sense. Like, I mean, that's why, you know, that's why Arduinos took off versus just like traditional microcontrollers, right? Because it was a lot more easy to play around with and to understand how to play around with, right? To get you know, specific projects done. So having that for the Hyperloop space definitely you know, seems useful. For you, Hyperloop, IITB, and then also for like the other teams, like which propulsion systems right now for Hyperloop, like the one of the teams that you've seen so far, whether it be university teams or companies, which do you feel are like really promising for large scale Hyperloop creation?
Swissloop is a team that I was extremely happy with. They made their own in-house, their voltage system was also approximately 800 volts. And they made a completely in-house inverter. And overall, the pod was so light, so optimized that it was just beautiful. So that is a team that I see closest to being commercialized. Like that tech is very close to being commercialized. So that is a beautiful team. Otherwise, I think all of the teams are doing really well. And this is a huge project and pretty new, so all of the teams are doing really well.
Nice, nice. And then, how about David? David or Mahek from UCI? What do you guys think is the like a linear induction motor that you saw that was really cool that you think that you wanted to kind of emulate, or you think will actually like be at full scale Hyperloop production?
To be honest, for our team, we haven't taken that much research into these alternate methods because we just don't we haven't had the resources, and at this time, because we can't actually manufacture, we're trying to get research going for future years because that's where we see the future of the Hyperloop concept. This really, the idea of using these like electric motors, it makes sense to accelerate the pod to a working speed for, say, electromagnetic suspension. But as a primary source, like we've seen the best teams use, it's only really coming out that way because the track's so short and there's not much going on, like no turning or anything like that. But as of right now, we haven't really developed into that. Looking at what at least I've found interesting are the different ways, like all of these maglev trains work, like how they handle the coils for the motors or either permanent magnets in the track. It seems expensive. Well, of course it's expensive, but it's sort of a feasibility question. I'm not certain how feasible some of these techniques are, so I'd be interested to see solutions to reducing that, making it more efficient, resource or cost-wise.
Can I just jump in on that? There's quite an interesting company that sort of have attempted to solve this problem. I think they're based in Spain. They're called Zeleros. And if I just share my screen, they use a sort of aerodynamic propulsion system for their cruise speed. So they have an axial compressor at the front of their sort of full scale pod design, and they use like electromagnetic propulsion for sort of launching the full scale pods, and then they use aerodynamic propulsion for sort of cruising speeds. So I thought that was a pretty neat solution that they had.
So that's also something that like I wanted to ask you guys about, like because I think that's another common point for propulsion, which is some teams swear by axial compressors and they say that it actually improves performance and it's important. And I think in the Hyperloop Alpha paper he mentioned it, and it was the point of importance. But then other teams, so like I remember at One Loop and even like I think we're talking to the University of Washington and other teams, and they were like, we didn't really see the reason like why you'd want to like have an axial compressor because you're in a vacuum-like environment anyways. So I guess my question is like, first from Hyperloop IATB and then to anybody else, do you think the axial compressor is necessary? Like, did you actually see any improvements? What is your thoughts on this technology?
Yeah, so hi Samarth. For axial compressor, we initially thought of using that, but like we ditched the idea because we don't have any particular manufacturer of that in India as of right now. And along with that, if axial compressor can be useful if we are working in like open air conditions, but as you said, in vacuum, we don't think it will be that much useful since there is very less amount of aerodynamic drag. So like we think it will be able to not give us that much efficiency with that, and rather than using that, using an LIM for that would be a much better option. Lekha, you want to add something to this?
Yeah, I think the axial compressors was to relieve the counterwitch limit that we see when there is a pod moving in a tube, right? That's what the compressor was initially proposed for. So since we are not actually using the entire size of the tube at the moment, and we are not exactly looking into meeting the counterwitch limit at any time soon, so we are not exactly uh, keen on using the compressor. And even if we are, I'm not sure about how much efficiency it will improve, and we might as well use some other technique to mitigate this issue rather than going for a compressor, because it is a much complicated design aspect and it requires a power source separately, and we may actually look into other aspects of it as well.
As far as I can tell regarding the use of the axial compressors, what you really need to consider is how, if you're going fast enough to get to that point where you're getting that supersonic flow over the surface of the pod, because then you run into the issue of the choked flow problem, which gives you that massive pressure gradient that's going to impede you. I think at first, most teams will probably not get close to that unless maybe they have really poorly designed aerodynamics, or, well, it's challenging, so maybe not so poorly designed. But once you get up to that speed, then that's definitely, I believe there will be something necessary to relieve the pressure gradient. Otherwise, it's just not, the fluid dynamics doesn't work out.
All right. How about Team Strathloop? Because I know you guys are just starting your research. What do you think so far? Like how, like what was kind of like your viewpoint on this topic?
I'll let Daniel Murphy, our propulsion lead, take this if you're about, Daniel. If he's not, I'll take it. But he would be our man to ask. Okay, looks like he's not. So we sort of looked the first couple of years at various forms of electromagnetic propulsion systems. We went for rotating Hall-back arrays in our first year, which turned out to be a bit of a nightmare. But then in our last year, we sort of looked into linear induction motors. And we kind of found over the past couple of years is sort of that it was not something that was sort of within the knowledge base of the people within the propulsion team. A large part of our team, or the overwhelming majority, is sort of mechanical engineering, and a lot of the magnetism stuff is not something that's taught until much later on in our degree courses. So we've really kind of steered towards more mechanical propulsion systems. So I think we're kind of really looking at things like the compressor nozzle or the cold gas thruster, or more simple electric propulsion that is a bit more achievable for us. In terms of the axial compressor chat as well, if I could add that I think it's not necessarily something that is going to work fantastically well for pod prototypes and over the distances that we are building pods for. But I feel like on a full-scale Hyperloop pod where you're having to factor in things like cabin space, it's going to take a large volume of the tube up, and you're going to experience the Kravitz limit far quicker, then I think the axial compressor then sort of gains a bit more merit in that department. So I hope that answers your question, Samarth.
Yeah, for sure. Yeah, seems like it's not really that necessary for most pod designs currently, because if you're looking at the SpaceX Hyperloop competition, but I can see how it can be maybe like really useful for if you're like actually trying to build a full scale Hyperloop. Maybe not for Hyper Poland or teams that are like trying to do that kind of a hybrid method, but definitely for your Hyperloop Alpha-esque papers and work where you're trying to like have a full vacuum chamber and whatnot. So I think the next thing like I wanted us to kind of discuss was so what are the things that you hope other researchers as well as the industry help with in terms of taking the propulsion to the next level? Particularly Hyperloop IIT Bombay. What do you think about this? What are the next steps that you want other people to do so that we can move forward and actually get this done?
Okay. To answer that question, you may already know that there is another team from IIT Madras called Avishkar, who are also working on Hyperloop. We are trying to establish contact with them and start working more collaboratively in the future. We have proposed this idea and we are looking to work together in the future. So I guess collaboration will be much better than just competing with one another, because this is a research and development project, and anyway, whenever there is collaboration between researchers is when we do much better than what we are doing on our own. So that is our first step that we are taking at this moment. So I would like to hear other teams what they are doing as well. We are also looking into industry collaborations. We are in contact with some companies for the research and development process in particular areas. So that's what we are doing.
I'd like to add that companies and student teams can collaborate in a much better way. Student teams can collaborate in a much better way amongst themselves. And companies can probably allow access to students to their testing areas or something. For instance, I know of an Indian company that allowed our Formula student team a small track that they use for testing their own systems. So my Formula student team was allowed to go and test their car over there, which gave us a lot of data, how the car behaves, etc. So something like that, but for Hyperloop could be extremely useful for all the teams in general, and overall get the research accelerated as compared to what it is right now. Also, it's a very new technology, so it's going to take some time for it to grow and develop. And of course, industries are going to take some time to adjust to it as well.
I would also add something here. So if you guys are aware about like TU Delft are like testing their pods in the tunnel or track made by Hard Hyperloop in Amsterdam itself, I guess. So some kind of companies which are available outside, if they are letting student teams or researchers to test their pods or research like in their particular labs or something, or provide funds to them, that will be much better way to like take this to the next level.
Right. Well, I mean, I was talking more about propulsion specifically, like from a research perspective. Like, what do you want? What do you think like should be improvements? Not from just your own team, but in general. Like, what are some open problems you think that if other people solved, it would help make your lives easier too, in terms of doing this research?
I specified about the one which was about the inverter specs, more transparency, and we should be able to tinker with the inverter in general, not just get it as a black box and just connect and go. That needs to be a thing that should be done. And in general, better transparency between industries who are interested in helping student teams as well to develop. That would be a very good idea, especially for our propulsion system, because we are having and we have been having quite some trouble when it comes to inverter choices and specifications. So that would be a good thing. Then, for instance, many other small services that a regular company can easily afford, but we kind of have to ask professors for it. For example, cell testing, state of charge, state of health, etc., cell characterization. So especially this stuff from electricals. So these little things, if a company is much more willing to help us out, we will ask them for help, and we will be happy to receive help in that way. So those are like two things these are two things, and these are the ways by which we can get help from companies, and overall that can make a very good system for accelerating research. I think Lekha can add more to this.
Yeah. Hello. Yeah. So, like she mentioned, yeah, inverter is a big problem. Like even one of the previous questions was based on that. Commercially available LIMs are not completely suitable for using with an LIM. So yeah, I guess that could be a area of research if an industry or any other team could get a head start on and is willing to help others to achieve the same results would be really good actually, because that is one of the areas where everyone will be benefited by research done, because I guess everyone is facing the same issue of inverters not being completely compatible with LIMs at the moment. I think that is one of the biggest part that we could focus our research on, collaborative research on.
I had more of a logistical question for IITB and other schools as well, especially if you're using technologies like LIM or inverters. I'm wondering how you're getting like your sources of funding to manufacture.
Like right now, we have a limited amount of support from the institute, our institute side. So as of right now, we have not yet like started manufacturing process. We are just in the design phase. So once we get into that, we will try to get more sponsorship from maybe companies or something in India, or also like we have this kind of contract or something you can say, when every year our institute provides us with some amount of money, so that we can like save some of it from 1 year and use it next year, so that maybe after 2 years or something we might have a sufficient amount of funds so that we can research more into it.
That's really interesting. I didn't know about that. Like, Yeah, I don't know about UC Irvine, but I know like at Davis, like we definitely don't have a model like that. I mean, if we ask for help, we can try to get some financial help from the school, but yeah, beyond that, like not like a continuous like yearly thing where you can like kind of save up,
Yeah.
And spend.
I guess
but-
we have like senior design, like as a part of the senior design project, depending on like the number of people on our team and things, we get like allotted funding from the school. So we do have that, but it's just that we've seen, like based on our like very preliminary research though, that some of this technology such as LIM tends to be more on the expensive side. And so that's kind of why we've not necessarily focused on that too much, just because as a senior design project, like one of our goals is to manufacture something every year. And so I guess we're trying to work towards research in new concepts, research and development of new concepts, but also keep feasibility in mind.
So, is there any like basic amount or like any upper limit for something like of the funds that they provide to you? Because we have that kind of thing.
What do you mean by like limit?
Like they will only provide amount of this particular level only, like maybe $20,000 or like $50,000 or something. More than that, they won't. You have some kind of cap for that?
Oh, I see. Well, we don't get nearly that much funding.
Okay.
It's more maybe like 5,000. But there's also like other grants at school as well. There's one for there's a fund meant just for technologies for green energy. And then we can get like another 5,000. So I guess there's not really a cap in that sense, but you have to apply for like different grants and like sponsorships. What about some of the other schools?
We have quite a similar model as you guys here at Strathloop. A lot of our stuff is grant based. I think a big chunk of our sort of funding at the moment comes from the alumni fund at Strathclyde. So we sort of apply to that on a yearly basis and get sort of pretty consistent grant funding through that. And then in terms of seeking other sponsorships, as Gregor, my teammate, alluded to yesterday in the Slack chat, we really go after sort of more in-kind donations rather than direct capital investment, which kind of can limit you in some ways. As sort of you can become a wee bit limited in the components that you can source. But for us, it's sort of the model that we go with just because of the situation that we're in.
I want to hear from one person right now, Mahmood. How's, because you were telling me about this last week we're having like during office hours. How is your team looking at building your propulsion system in Egypt? Have you kind of like talked to different companies about like potentially sponsoring, or are you trying to just like build it from scratch? What's your plan so far?
Our propulsion system built on brushless DC motor. We chose that because we haven't a manufacturer for linear induction motors and also axial compressor. And this is our first time to build a Hyperloop. So we started from scratch and trying to build a robust base to build on top of it. That's all. That's all. That's all.
Oh, so sorry. Like, yeah, you kind of talked about it yesterday. So, but like, are you going to so are you going to like potentially make a limb one day, or you think you're just going to like continue testing with DC motor and kind of see what the competition, where the competition takes you and whatnot?
For this year, we will still using a brushless DC motor. For next year, we don't know, but we're trying to manufacture a linear induction motor, and discussed with some companies in our country to bring that from China, and we're trying to get more and more efficient propulsion system.
Interesting. That's definitely yeah, an interesting model.
But how do you plan to test it?
We're trying to call with our government to give us our IPM based on competition standards. But now we're using MATLAB Simulink simulation for testing for our targets, and we reached our target. Our target speed and RPM we reached based on our simulations using MATLAB and Simulink.
Oh, okay. Thank you.
You're welcome.
Okay, so I mean, like Hyperloop IITB zero panel, but just to say like to see like what kind of what's been discussed from what I understand. Yeah, there are some changes you guys that can be made to the limb from a research and development perspective in terms of frequency it can reach and making sure that there's not as much impedance at higher voltage. But it seems like you said, like a lot of it is more still like human part of it and not necessarily the technology part of it. That like if you could work with a company that like could build that and they could keep it open so that you can actually like develop it properly, then you could effectively build a really good limb, and it should be able to scale. Is that kind of like what I'm hearing, or was there more to that?
I think that's pretty accurate. I think the biggest difficulty associated with the limb is just the sheer amount of windings that you have to put in those teeth.
I think we would attempt to purchase a limb. The issue is we've had a lot of difficulty securing funding, so that's out of our reach for the moment. But as Ryan said, we built Ryan built a coil winder for the limb. Due to COVID, we haven't really been able to wind it, but we attempted to build a limb a couple of years in the past, and it just the way it was designed. This was long before I was on the team, but from what I've heard, at least, the issue was because of the sheer amount of winding, people kind of ended up cutting corners or didn't turn out right, and we definitely don't want to do that this year. So we're going to put in the legwork if we can't buy one. That said, assuming our business team does their job, which I certainly hope they will, they're very talented members, we won't have to do the winding ourselves, except for the prototype, in which case we will have to do the windings.
Yeah, we'll do it.
We'll do it for sure. I'm very lucky we got some very talented members on the team.
Agreed. I mean, it kind of depends on what I decide on the system. It depends on if a manufacturer is actually ready to give it to us or not. So for instance, the manufacturer says, no, we're not going to be able to make it. I might have to scale down on the voltage, probably look for a different system altogether. So I think the first problem that we have to sort out is the fact that can we even get in real life, can we even get an inverter like that? Can we even get the resources for a system like that? So I need to sort those out because I might have to change my designs just based on the fact that I cannot get some component. So that is a major thing that we're currently focusing on since we're a pretty recent team for now.
Makes
Would
sense,
anyone
makes
else
sense.
like to weigh in?
Okay, I think that's I think that's good for now in terms of the discussion on propulsion, unless anyone has any last comments. But it seems like, yeah, I should have invited more propulsion companies. I mean, we try to talk to quite a few different companies who are manufacturing limbs and doing that kind of work and see if they could potentially show up. But yeah, we'll try to get more in touch and see like if they can, make these changes and make it possible for us to build this, because seems very doable. So it doesn't seem like the technology is necessarily the limit at this point, at this exact point. I think once we get everything open, like once your team at Hyperloop IIT Bombay and our team at Davis and Strathloop and all the other teams participating today, once we all have limbs that are like, or that we can like tinker with and play with, I feel like then we'll actually be able to make real progress, because then we'll be able to like kind of play with each other and say like no, like this was how much I actually set the sunset to, like no, this is how much I actually like, and then it's really the problems of the beams and everything else, right? And not as much the limb. So yeah, I guess let's leave it there for now. Let's take a break for 15 minutes and then let's talk about controls. If you have any questions in the meanwhile, just feel free to unmute and ask, or ask in the chat, or ask on Slack, or ask on Facebook if you're watching on the live stream. Hey guys, for anybody who's around, like I was looking at one of the questions on the propulsion panel, which was like, yeah, what are the different suppliers? And I had an idea. I just really briefly, if you guys like wanted to see what you think, but like what if I think different teams like are in different geographic areas that have like different companies that are doing different things. So what if teams form like partnerships with those companies? So then the company gets to, so like two teams and like one company or something like that. So then that company gets to say that they worked with like two teams, and then like that company is also more comfortable with the teams because they already like worked with one company, or they worked with a team that was like in their local area. So they speak the same language. They can at least meet up once in a while. Because I think like there are some really amazing companies in like Europe and in America that not everyone else is getting access to. And then at the same time, there's also like a lot of really scrappy startups in India and whatnot that like a lot of teams in the US don't even know about, right? Just a thought.
That's really interesting. Can you hear me, sorry?
Yeah.
Okay. That's really interesting. Is when we were pursuing induction motors last year, just briefly, we contacted several companies in the US as well, because in Scotland we don't really have as many. Our options are mainly either down in England or manufacture our own. And we contacted some in the US, and we were told that they have like clashes of interests with other teams, and like that's understandable. But that's a really interesting point you make, because we have a team it's away from Glasgow. We have a team in Edinburgh that hyped. They're manufacturing their own, but if they were using suppliers, it'd be quite helpful to be able to like form alliances, like you say, like that, rather than just using the excuse that it's like conflicts of interest. So yeah, it's a great idea.
Yeah, just a thought, just because like nobody's spending their own money anyways, right? Like no team has profit, right, or revenue as such. Like everyone's getting grant funded, right? So if you're getting grant funded and that's actually what's paying for it, might as well like just, yeah, it'll look better for the university too, that like they're working with, you're doing like a research partnership than just like one team going and doing it. And then if hopefully that'll make the company like want to actually give you more stuff, because they see it as like helping the ecosystem and helping universities. But
yeah, I definitely agree. I think you're right about because where the funding's coming from, and it's all good intentions. It's not as though it's like a competitive kind of environment. Like, of course, to some extent it is, because we're trying to innovate, but we're all trying to innovate towards the same thing and a common goal. So no, I fully agree with you.
For sure. All right, well, it's end of break. So now we're gonna go into controls. So based on yesterday's panel presentation and paper write-up, the moderator for the controls panel will be Mahmoud Nasser and the team at Welner Hyperloop. So Mahmoud, if you want to go ahead and begin, then please get started.
Yes, the sound is clear. The sound is clear or not?
Yeah, we can hear you.
Yeah, got you.
Okay. Good evening, all. Let me introduce myself first. My name is Mahmoud Nasser, control team head at Welner Hyperloop. Welner Hyperloop is an Egyptian team that has been established this year with a goal to design a Hyperloop prototype to participate at SpaceX bot competition. In our next 6 months, we hope to manufacture our designs and make a fully manufactured pod to participate at SpaceX bot competition, and also build a new team to continue our journey and spread the idea of Hyperloop more and more. We want to be the first Egyptian and African team that designs the pod to encourage others to build their pods. This will be our first step to have a robust base that could build on top of it and have one day a hyperloop that connects all African countries with each other to enhance transportation methods for passengers, goods, and so on. Challenge we faced: we want to build a wireless network that connect all systems with each other without any wiring problems, and also could access the pod data from anywhere and interact with. So we worked on this target. As IoT is getting increased more and more through the past years, and there is a great progress in many IoT fields like wireless network, gateways, carrier networks, and IoT platform. So we build our prototype to test and prove our concept that based on testing, we will know how our design works. For example, we select our wireless network gateway carriers network that have less energy consumption and its bandwidth suitable with our design. And as you know, there are many wireless networks like Bluetooth, Sigfox, Zigbee, LoRa, and so on. And also gateways providers like Cisco. And as you know, the gateway is more powerful if it supports many technologies. After our consideration, we will choose our suitable one due to its power consumption and suitable bandwidth. Unfortunately, due to coronavirus, our manufacturing has been stopped, so we are still waiting the factories to back on track again. We design our full control system for the pod and trying with simulation to reach the optimum point. Now, I will talk about an overview for our system structure. Our system structure, let's start from bottom to up. Firstly, sensors on board. In order to have a robust system, different sensors have to be established and distributed around the pod. Sorry, to measure all parameters in which the action the action will be taken based on their values. Then our system controllers. There are many microcontrollers suitable for us for each system to take a sensor's data and takes action based on it. Onboard computer. Our onboard computer will act as a brain of our pod that all systems connected to and monitor their performance and also interact with them if there is any problem. Our sensors on board, there are many parameters that should be measured like distance, temperature, pressure into the pod, and the position of the pod at the IP. For example, temperature of batteries should be measured as possible as we could. So we could, because of lithium batteries hazard, and also the position of the pod on IP should be measured to know the position of our pod. System controllers. There is a controller for each system to manage and control it. For example, the navigation system is measuring the distance traveled by the pod in many ways, like using incremental rotary encoder and fusion sensor, and send all these data to all systems to know what is the current state of our pod. And based on the data sent for example to the brake system, we know when it could apply the brakes based on the distance traveled by the pod and also our brake distance. We will use Node MCU for its advantages like integrated ESP chip and supporting TCP/IP protocol, which we will see how it will work with us, help with us. We will communicate between systems using machine-to-machine concept. It's the way that the devices communicate with each other. The machine-to-machine concept is divided into two main categories. The first one is local machine-to-machine, which all devices communicate with each other locally, but I won't know what's going on. So we build a local server that connected to them over MQTT protocol, which is a light protocol suitable for small data. The MQTT protocol make a MQTT broker. MQTT broker acts as a virtual wallet that stores data. All clients or devices send the data to it, and any system could access this data at any time. And also we build our dashboard to display all sensors data and also could interact with pod through it. For emergency systems, we connected our critical system to an IoT platform for being safe side and communicate with our onboard computer, which is Raspberry Pi, through a remote desktop access mode using port forwarding. We also trying to apply a new concept, which is off-board diagnosis. There is a onboard diagnosis in automotive industry, and also the new one is off-board diagnosis. We're trying to apply it using MATLAB and Simulink and Raspberry Pi and Amazon Web Service. We build a mathematical model for our bot, which is running into the cloud, and Raspberry Pi takes all these data, input and output data, and upload it to the cloud. And on the cloud, there is a comparison between data comes from sensors and the model that we made. The data comes from sensors and the model we made running on the cloud, and based on the data comparison, the action will be taken. This is our next challenge due to low memory and the processing of embedded ports that we go to off-board diagnosis to use that. And at the end, I want to thank everyone in my team. You did great. We were only 8 persons, and despite that, all what happened as a new team and coronavirus, we reached to a final design that need only 2 manufacturers. We're using softwares to test it. We used ANSYS for finite element and CFD. We built also a mathematical model for that, for our board, and also trying to apply off-board computer, especially in our cooling system for batteries, to compare the current temperature of batteries and system state of charge to the state of charge based on the cloud model, and that the action will be taken based on the comparison between data. And let me share my screen. And this is my team. All of them did great. This is our first time to make decide to make a Hyperloop prototype. We don't know anything about that before. We tried from scratch. Then we reached to final design that we could apply and join the competition with it. If there is any question, I am here. Hello?
We can hear you.
Hello?
Yeah, I guess I just had a question about your concept of off-board diagnostics for with using the Raspberry Pi as your base computer. Have you considered any other like microcontrollers at scale, or are you still planning to use like Raspberry Pi when you actually like go to the SpaceX competition as well?
Look, I decided to use Raspberry Pi. Due to the camera, we will fix a camera in the front of the bot, so we will have a live streaming on what's happening on the tube, and also I could connect Raspberry Pi to all systems controllers, which will make me could upload any new orientations code or anything that to my system controllers over it. So I have a computer based on my board and could do whatever I want at any time. and at emergencies, I could interact manually if all automatics failed or any failure happened. I could upload a new orientation, like in satellites. If a satellite missed its orientation, they could the control team could upload a new orientation to it to onboard the computer that established on it, and back on track, on the right track. Because we are new to, also we are new to the competition, we try to be in safe side as possible as we could. That's all.
Okay. I mean, I think that what you did is like I mean, like from my little understanding of controls, sounds you know, pretty good, and sounds like a great way to get started. Curious about the other teams though. Like, are you like, for example, Strathloop, are you guys also using a Raspberry Pi and your own local server, or are you planning to also go the route of AWS and off board, or how are you managing your connections to your pod?
I can't speak entirely for navigation and control. We don't have someone from that team here. I think we're looking into using Arduinos just now. But other than that, we can't really help out. I think Sam might be able to give you some more information. I'm not sure.
We use for navigation system Node MCU, as I told before. Due to its integrated ESP chip, which will support TCP/IP, we could connect to Wi-Fi network. And our navigation system, we try to build it in 3 ways. First one, using incremental rotary encoder, which is fixed on the coupling with our final drive of motor, and calculate the distance based on that, as you know, the pulses. And the second thing, we use a foundational sensor to detect the colors strips around the board. As you know, there is colors yellow and red. The third one is using a camera. If any problem happened, we could see what happened inside our board, our tube. So we could interact if the whole brake system failed. We have an emergency switch on our local web server that could interact with the board directly and cut off the power to it.
So one question I also had for anyone who's working on it right now is kind of integrating what we were talking about before with inverters and propulsion systems. How configurable are you guys keeping your inverter and your propulsion system to your controls? Are you integrating it fully, wherein like your exact you have like VFD or something similar connected to every single part of the motor, and you're driving every single magnetic component, and you can stop every single magnetic component individually if needed? Or is that all on like kind of like a black box, and you're just going to connect to that black box via controls? Kind of what were the thoughts that you had about controlling to the different coils on the motor? Because I know, I guess, Mahmoud, if you want to start by saying like how you're controlling to the motor right now with DC, since you're doing something different propulsion-wise, and then if anyone can fill in on limbs, that would be great.
We have a strategy for our propulsion system. We use the brushless DC motor, as we trying to build a base, robust base then we could build on top of it. Hello? Hello?
Yes, you're audible.
Connection. I lost connection. Please repeat your question.
I was
You
asking
were
about.
audible.
Oh, okay.
I just said
He
he
was
was
disconnected
audible.
for me. All right. So I guess like just to repeat the question, because I think you disconnected and then I disconnected. I don't know. So
I don't know.
But I think the question was like, how do you
controlling our propulsion system?
Yeah. What are you doing for that?
We have two strategies. First one, we could control that by connecting the system as a motor controller. As you know, we use the brushless DC motor. We could connect the controller directly, which is manufactured from the company Kelly KIP. We use its controller and open its software on Raspberry Pi. And in the access mode, we could interact with motor and changing parameters at real time. This is a strategy, that ideal strategy. And the second scenario or strategy we put, we controlling the power come to the motor from batteries, and we have a track strategy for us based on our throttle. I don't think the screen was with me now. Throttle figure, how we will work with motor. We could work with cruise control to make a constant speed that the motor work on as our track strategy, and have a constant time to finish the track on. We could also control the power come to the motor from the batteries by establishing a parallel relays also on the power lines, and controlling it using node MCU on or off the power. This is our strategy.
I see. That's pretty interesting. Yeah. So I guess like other teams, how are you trying to do? Well, I guess that's the problem. Those are the two options that you were bringing up too, right? Like using the kind of black box controller, or doing like, you know, direct relay access. So yeah, curious to hear what everybody else has been doing. If you're looking at a black box or you're connecting to the actual individual components of propulsion.
Hello. Yes, One Loop here. I have some interesting points on propulsion based off of the inverter system that I'm developing. There's actually two simultaneous control systems occurring for running the limb. One is based off of the optimal slip of the induction motor to generate the maximum amount of torque. And that can be derived simply by differentiating the torque equation in terms of slip and essentially coming up with an equation for drive frequency that is a function of only like essentially pod velocity. And it also has two constants which are unknown at the time, but should be enumerated through actual like testing on a test stand induction motor setup. The second control system is a current mode control system and is essentially a PI controller that handles like essentially current limiting, and it should regulate the current to whatever the set point is up until like a maximum where you know it simply can't give any more current. And then there's also certain overcurrent protections in place as well. Yes, that's our control system.
We also build a PI controller for our system, for our propulsion system. I will share a screen from screenshots that we take from our model. Here is the data of our motor RPM to torque table. We make a lookup table that we have a target speed and torque. We're trying to reach that. So we build our model to get this target. This is our this is our throttle signal based on BI controller. It will be like that. So we limited our motor to our target speed. We don't need the motor to reach a high speed rather than we want. Kelly controllers make this advantage to make a maximum speed, and we set on our cruise control mode. So we have the ability to make a constant throttle input to the motor. And this is the atomic view of our motor. We build a cruise control for our target speed and measure speed, and we have to compare between them. And we could in future generate working with the code generation and generate a C code for our controller based on the model, and have our own controller. We set up two parallel systems with each other. One of them using Node MCU, and the other is a black box controller, which we get from Keliki IP. That is all. If there is any question.
Yeah, so in your overall control system, have you considered lags in communication, considering you'll be using a cloud system?
Yes, we take in our consideration that we put a safety factor for each system. For example, navigation system, we put a safety factor, highly safety factor, 10 meters accuracy. Also for brake system, we make a huge brake distance. For first testing, we missed real testing due to the manufacturing stopped due to coronavirus. We designed our wheel and body, and the frame manufacturing stopped, and we manufacture our lateral control module. After the factories gave us the permission to work again, we will finish our design and trying to test it using I-beam that we will take from our transportation ministry to try to show our prototype result. It will meet our simulation result or not. What is the difference? Where is the problem? We should do that to verification step.
Okay, thank you.
Yeah, you are welcome. Is there any question?
Hello, I'm Adrian from the University of California Irvine's HyperX, and I wanted to ask, what are your advantages of using MM over a more traditional thing like serial connections?
The sound wasn't clear. Please repeat.
It's
I'm sorry.
okay?
Maybe.
Maybe, okay. Well, I wanted to ask, what is the advantages of using M2M over a different protocol like serial?
Yes. We don't know. Firstly, this is our first year to build the Hyperloop prototype. So we have a fear of a vibration or something what could happen inside the tube when the pod start to run. So we tried as we could to make a less wiring for all systems to to avoid miscommunication happening due to wiring issues. And also machine-to-machine concept make us could interact with system controllers and show their data over a wireless network. We could access data at any time and make it simple for us as a ground station laptop. Hello?
We can hear you.
Yes?
Thank you.
You are welcome.
But a lot of the other teams are using Serial, right? I mean, I don't know much about this field, but like, yeah, well, the rest of you guys are using Serial, I'm guessing, or are you using M2M as well?
Well, we're using
Yeah, that is
something similar to serial called SPI, but it's another type of serial, so sure.
Yeah. And there is error handling, highly error handling that we have.
Well, for the battery module, which we'll get to in a little bit, I think the next section, I'll talk about that. But essentially, it uses cyclic redundancy checks after every SPI communication.
Yes.
Okay, what do you want the controls systems of Hyperloop to look like in the future? Because I know you were talking about immediately for the Hyperloop competition, but like moving ahead to like, what are some areas of help, or how would you improve?
This is our short target, term target, Hyperloop bot competition, but our target, a long-term target to, as I said, to build a Hyperloop that connects all African countries with each other. This is our aim. We are trying now to build a robust base to the next team could build on top of it. We try as IoT get much progress every day in many fields like gateways. Cisco make a huge gateways technology, carrier networks. Now we have 4G, 3G, narrowband, Sigfox, many more technologies. So we could use it with Hyperloop full scale. Any passenger could know where is he now, as it will be in closed tube. How much time to its station, how he could book the ticket, and for controlling technical issues, handling from the Hyperloop team which work on it. They could, as you wanted to go to figure out the problem on wiring, they could also figure out the problem wireless on the control room, figure all things they need. As I told you, as I told O-board diagnosis will play a great role on that, comparing all things with each other. So you don't know to know you don't want to go to the pod. You know everything about on your place, temperature, pressure. If you has any disease about low pressure or anything like that, you could know the pressure into the pod. Make you know everything about the pod for a passenger and the technical engineer. Every one of them in his role.
makes sense. So another area that I've seen like some teams take a look at, and I think even Loop was interested in at one point, is machine learning and artificial intelligence, and seeing
Yes.
how we can use that in improving our pod control systems. What is your take on this? And then, to everyone else, what do you guys think about using these technologies? Does it have a place in Hyperloop's future, or is it kind of a bit over the top?
Yes, we tried to build a model, a machine learning model for temperature prediction, but unfortunately we haven't complete the manufacturing. It needs data. We haven't it. So the next step for the next year, the team will continue. As you know, this is our final year at our university. The team will continue the work. There is a sheet for the future work. They work on it to continue the journey, not starting from scratch like us. And we in the field of machine learning and data analysis, off-board diagnosis will help us to analyze all data that the Hyperloop for the last month. For example, for the last month, we know when the temperature got high, when it decreases, how to handle it. All of that we have a large data based on the cloud, so we could make analysis techniques to it and figure out where is the problem. In the other side, onboard diagnosis, you don't know the history of the vehicle. You have the problem of that. So now you have the history of the bod, and could take an action based on analysis of this data, which will help you to figure the problem, predictive maintenance, all these things that could happen, could be working on the future, especially predictive maintenance. All of that could be applied. Is there any question?
Sounds good. I mean, I'm just wondering what Mahek and Team UCI, or what I thought I saw like you guys were working on something in machine learning before. What's your take on this for controls and controls development?
I don't think we're really focusing on that right now, but Adrian, did you want to talk a little bit more about our control system?
Oh, wait, can you repeat that?
Yeah, I was just saying that I think I seen like that your team was thinking about using machine learning or other methods of predictive analysis in your control system to improve upon itself in the future. What is your take on machine learning and Hyperloop? Does it have a place in the development of technology? Where does it have a place? And what do you think needs to happen to make it more possible, I guess?
Well, I think there's definitely a place for machine learning in almost every industry because it can provide valuable optimizations to just further like improve the performance of every piece in the puzzle. But as of right now, we're not thinking of implementing just yet because we're still in a more construction phase right now. We're still ordering parts and finalizing every detail. And I don't think until we get everything set in stone, we can start thinking about machine learning. However, once we start finalizing everything, we might find a place and decide to see if we can improve our pod even further.
Makes sense. Makes sense. Sam, Strathloop, team. Y'all have thought about this or not really?
It's not really something that we've put too much thought into. I think we are still in the process of sort of trying to work out the pod controls at our scale, never mind on a broader scale. But I certainly think, just talking from sort of personal opinion on Hyperloop, in a sort of scalable sense, one of the big advantages of making a new form of transportation is you can add sort of these sorts of cutting edge tech to really try and optimize it as much as possible. And I think sort of having automated control systems for Hyperloop is a really sort of critical part of its success, I think.
Makes sense. Kurt, did you have a question?
Oh, yeah. I had, I guess, a couple of questions, really, for Hell One. So, if you are testing IoT right now, is this something that you expect just to facilitate your team's development in setting up development infrastructure for your continent, or because you want to access other external cloud-based resources on other continents? And that really has like this other caveat with, you know, what do you expect would be appropriate infrastructural overhead or cost for using IoT services primarily for development and operations of something like that?
We try to apply to try our concept that we put of IoT using very basic microcontroller like Node MCU, and trying to apply the IoT concept on our prototype. In case it has a good result, we could try it on our large scale, or design our infrastructure. We could do that based on the result will come out from prototyping. We are in prototyping phase.
Sure. I guess my question was, you know, is IoT
maybe a problem? Sound isn't.
Yeah, I can. I'll repeat his question because I was curious about this too. As you scale, right? Like right now, it's not the big of a problem, especially if you have a test track that's on your campus. I'm sure that's not connectivity is not an issue. But your goal is you want to build a Hyperloop for Africa, right?
Yes.
So when trying to do that, you still are saying you want to use cloud services for managing the teams, for managing the
pod.
Yeah, for managing pod. So are you going to try to use cloud services outside of Africa, because AWS and whatnot doesn't have infrastructure in Africa, from what I know, right? The nearest one is
yes, I know.
Middle East. So how would you scale that? How are you thinking of scaling would you have to develop the communications infrastructure to be able to build that Hyperloop out?
If we talk about IoT deployment app, we will make our unique one. Maybe we will not use Amazon Web Server. I'm talking now about the large scale, full scale Hyperloop. There is many. You don't know how many things that prohibited here. LoRa is not work here. So we tried to approve and test our concept with things that exist and available for us. So for scaling for large Africa, for full Africa, we trying to prototyping Hyperloop pod, largest small scale pod to try it in the SpaceX pod competition or testing on our camps. If the concept is right and the result is good, we will try to apply it on the large scale, but which is available and could be applied on our area or region. Yeah, we could use if we wanted to use the LoRa wireless network, but is prohibited for us, but prohibited in our region. So we couldn't try to we couldn't use it. And so far, many things that happened. So we work with the things that existed and available, and makes no problems for us or our camps. This is all the story.
Kirk?
So I guess this, maybe I'll just like reiterate, a little bit of the prior question in a different way. Do you think the way that you are testing out IoT, because it's easy and available for you right now as a team, is a good test or measure for how other African Hyperloop teams may also do their development? And thus, would IoT be a good way of doing Hyperloop development, prototyping in Africa? Or would you like to see other types of prototyping environments made available because you think it's better for how other local teams should develop in your area?
I will tell you what happened with us briefly. We talked with with Saudi Arabia, which will make an Hyperloop full-scale Hyperloop, as the news said. We tried to reach and United Arab Emirates. We tried to reach out and connect with them. We talked really with one of them at United Arab. They told us they didn't make the old technology that for the Hyperloop. They take what's suitable for them only, and then they developed that on their scale. This will happen in Africa. Here we have only team in Africa that make Hyperloop or will join the Hyperloop SpaceX bot competition, or only decide to build a Hyperloop. So we have in the community that will help the idea to be spread, but we talked with our transportation ministry. They honestly tried to help us, but the availability of things that couldn't be occurred. So we tried to reach our goal with our local available things. That's all.
Yeah, yeah. I think his question was more like, so yeah, you've done a great job and you have a great system like now, and hopefully you can test it out as a coronavirus weekend grip on the world. But to make Hyperloop possible in Africa, like how you were saying, do you think the IoT method is what other teams in Africa should do as well? Or do you hope that other teams in Africa will bring new solutions to controls and development?
Everyone could have a new solution. We have a solution. Other team could have a solution. We have here around 4 teams. Each team has a solution for its design, for its everything he wanted to do. So if we talked about the large scale in Africa, there is a Russian company that tried to build a train that connected 10 countries in Africa. So this is make an encouragement to us to be trying to apply that for Hyperloop, not for a fast train. This is a motivated thing for us, and make us motivated to work on Hyperloop. The point of IoT, we chose IoT because the many technologies that appears nowadays helps us to achieve our goal. And then IoT, everything is connected now. Mobile, cars, trains, everything is connected. So the Hyperloop as a IoT is going more and more increasing and using everything is connected to internet. And many protocol, other protocols also you could use based on the application. In desert, you could use Sigfox, and for large distance, you could use what's suitable for you and your data. So the IoT gave us the capability to make a huge progress in our work. That's all.
Okay. Then before we move on to another topic related to controls, I was just curious. Hyperloop IIT Bombay. I know that you guys have probably thought a lot about Hyperloop development in your area because of Hyperloop 1 coming in and trying to plot that route, and your government trying to plot that route between Bombay and Pune. But you have a lot of the same problems infrastructure-wise, right? Since you're like developing
Yes, we had safety
new
issues.
infrastructure, safety issues. So but particularly for IoT and for controls, how are you going to approach?
So my priority for onboard computing and communications will be speed and efficiency, because I want it to be as robust as possible and as accurate and error-free as possible. So definitely I'll be using error reduction mechanisms to reduce noise in the sensor readings, etc. I will be focusing on speed. So in case I will be using anything like machine learning, it will be on data which has already been gotten from the pod after a few test runs, after a few simulations, I guess. So that is something I will be using ML on, or any other advanced techniques. But on-pod communication, sensing, it will be as bare bones and as fast and efficient as possible, because the pod will be very fast. So even like a small lag, which looks small, can actually be catastrophic for us. So that's why.
Hello.
So those are the priorities for now: robustness and less noise.
Hello. Can I speak?
Yes.
Yeah. What for to apply ML in any what are the basic of ML concept is that you have to have a lot of variables, right? So the basics of ML is like you have like statistics is involved, of course, like statistics and probabilities involved, and a lot of programming languages involved, and not only that, what a lot of machine learning model to optimize the pod, we have to apply a lot of machine learning models in that sense. But how are you generating the data in that sense?
The data will be from prototype tests that I will be doing, but that will be like after COVID and when the uni start, when we actually get back to the campus, etc. And most in case I have to use ML, I'm not sure if we will be using it for now. Frankly speaking, have not thought so. I haven't considered that far when it comes to controls.
I see.
But if I will be using ML, definitely it will be on data that I will get out of small testing sessions I might have. For example, maybe I'll just run all the sensors. I just put all the sensors on the floor on a mat and just run all the sensors, trigger the sensors, see how much readings I'm getting, etc. It doesn't even have to be a full pod test. It can just be a subsystem test or something for the data that I'll be getting.
I see. So what my another question is that a lot of variables will be involved, right, for
Yes.
to optimize. So what not only that, what do you say? You said a lot of sensor data is involved. Like you can actually like a lot of ML can be used anywhere actually. Like for transport. It's a like you said, it's a far-fetched idea actually, but it's it will be good actually to optimize the pod using ML actually. That's my whole take on.
Yes, but for that, first I'll have to freeze on the overall pod design before I actually optimize the pod. I need to get an overall pod design, be it electrical, mechanical, propulsion-wise, etc. I have to have all the facets completely sorted before I actually go about optimizing my pod using ML. I think that would be like a later stage for our team.
Thank you.
Considering we're already in a design phase for now, so we'll optimize slightly later.
Thank you. Like not only for the mode. I think what do you say, when you apply ML, the thing is that each when you like how can I explain this to you? Like not explain. How can my take on that is actually like each run a lot of new variables will be arriving, and each run will be different from the previous one, right? So a lot of data will be generated from there as well, right? So
correct.
So what was your take on that then?
A lot of data will be generated, and yes, when I actually do end up getting that data, I will be using it for further pod optimization. I will be using models. That is a given.
Yeah, that's a given.
In fact, even experimental data will be used. I mean, that's pretty obvious for me right now that yes, I will be using models on the data I get. But for now, my priority is that I have to have a system that even generates the given data. That actually works, and I get the data that I want in the first place so that I can use the models and get some outputs, get some answers to the problem statements that I have in my mind.
Yeah, basically like what do you say, all ML models are like that actually, like without having the data you can't work actually. Yeah,
exactly. So for now, all I have is simulation results, mathematical computations, and well, in the real world, simulation results are often shown to be inaccurate. And mathematical models can only get so close to reality.
Yeah, the experimental data that you're generating via software, like either in MATLAB or ANSYS, those are experimental data. You're not actually physically seeing it, and then only you can. Yeah,
exactly.
Yeah. Thank you.
Yeah. Any other questions regarding our controls, electricals?
Thank you. Not for Hyperloop IITB, but just a general question. Is anybody aware of research papers for software in Hyperloop, or has anybody found anything like that?
I just look for research papers for some certain topic that I need help on. I mean, I don't exactly search for Hyperloop. So if for example, if you're looking for linear induction motors, for instance, that is a search term I'll be using. I probably won't be using Hyperloop because I don't get a lot of hits when I look for Hyperloop specific papers. Or I probably searched way long back and that's old information. But I usually prefer specific terms to like Hyperloop papers.
And I'm sorry, yeah, I think and also my question is like, for control systems, are there many research papers that, talk about, very fast, speeds and stuff, and anything you can use in that regards, or is it more just like hacking your own systems together and trying to get it to work?
A lot of it is hacking my own system together. There are papers, they exist. For example, so as of now, I'm planning to use CAN, and there are research papers on CAN. So of course they exist. There's research papers on these systems. I mean, these systems have been around for quite some time, so definitely they exist. And otherwise, regarding Hyperloop control system, I'm not sure if I have found a paper so far. I cannot say that no paper exists because I haven't really looked that hard, but I really hope some paper exists. That will be pretty useful because the communication speeds, because over here the speed and error reduction mechanism is something that's a priority for me. Even if my system is takes a lot of power, for example, But if I end up getting a very good speed and very noiseless data, I will take it.
Thank you.
So that's the design priorities.
Actually, I found out NASA did a feasibility study of the different systems. You can get the PDF online actually. Like it's a way old about feasibility study. Like when
Yes.
you can find that online actually. NASA did a feasibility study. What is it possible to travel at this speed, and what is general like they did a feasibility study like in 2017 around 2018. So it's like they were interested in applying the existing whatever I had proposed for Hyperloop into their existing technology for their space program. So you can find that online. The feasibility study.
That's interesting.
Yeah. Not only that, even MIT also did a feasibility study actually.
Yes, that's something I'm aware of. But like, those are feasibility studies. I'm not sure about full-fledged research papers. I'm not really sure about them. I didn't specifically look for Hyperloop, to be really honest. I was more looking for individual systems. I was not specifically looking for papers that mention that so-and-so system will be used in Hyperloop or is feasible for use in Hyperloop. But yeah, that sounds like a good idea. Thank you. Thanks a lot.
No problem.
Yeah, I was just actually looking at the MIT paper right now, just again. I remembered like them talking about it, but in theirs is like it's on like the lateral control modules, it's not actually like the software as such. It's more like how it's keeping it like the stability control, not as much the software. So
that's true.
Yeah, definitely could be an area of improvement if people can write papers on like how to ensure that speed up. I know that like we were talking to Gator Loop, and they had like some neat system that they were trying to come up with for pod management, and they were trying to scale that so you could like so that Hyperloops would be kind of like how we have our central control systems for subways, but like even more optimized. But yeah, like definitely a lot of improvements that need to be made at the first levels of access, right? Like accessing the motors and whatnot, before even getting to any of this other machine learning and improvements.
Yeah, I've just got an open question for any of the members here that are kind of part of the design of control systems. So I'm much more focused on the kind of mechanical systems and the hardware design. So how can myself and other members that are more focused on hardware design help out the kind of control systems in the way we design our systems? Like, what kind of things do you guys look for in terms of good control?
So if I got to answer this, I would probably ask for a very good mounting for my sensors, because a lot of the time vibrations end up making the sensor data very noisy, which is pretty hard to then remove the noise and then process the data. So that's a bit of a problem. So that is one. And overall, just give us enough space to work with on the pod, and have very nice conduits for wires, for example, because there's so many cases where I've seen that due to some mechanical part, the wires got snagged, and there was noise because of the wire getting snagged or the wire having a mechanical problem. So a lot of the times, mechanical issues create noise in sensor readings, create noise, even help making the problem of HV noise even worse. And that's how. So just mounting is a way you guys can really help us out, and just giving us enough space, literally.
Cool, thanks very much.
Okay. I guess the question I had for HyperExcite and one loop was same thing pretty much that Shreyashree was talking about. How is your spacing for the controls done? Because I remember that was also an issue that we had at one loop to some extent.
Well, actually, we haven't come across that just yet, but in all reality, we should start planning for it, see if we could avoid the problem before it starts. I'm actually discussing with my team right now on how we can mitigate these issues, but we don't have like a dedicated way to prevent these mechanical failures.
Mira, one loop. Well, I know you guys are going to talk about it probably more later, but like any problems with spacing due to controls?
With what did you say about controls?
With spacing, were there any issues with spacing in terms of being able to fit control systems in with everything else?
So the issue, and Ryan, you might know something about this that I don't, but we're still in the process of figuring out which PLC we're going to use. We're debating between a Rockwell. We want to back off. We don't know if we can get funding for it. That's as you can see, that's a recurring issue for us. We might also be using a Rockwell. So we don't have all the information we need yet to figure out what type of spacing we're going to need.
For last year's pod, that was a little before my time, but I did get a chance to look at it. And I can tell you that the PLC was presented nicely in the front of the pod, and right behind it was just a mess of perf board and Arduinos and wires. And that's certainly an area of improvement. You can't have just a bunch of wires laying around willy-nilly. You gotta have some wire management skills. You know, you gotta strap them down and keep them organized. So
SpaceX actually had issues with how we presented our wires last year, which is pretty understandable. They were indeed a mess. But they said that not only were they too messy, but we had more of them than was strictly necessary. And we had more, the amount of redundancies we had was so much that it was actually hurting our performance.
That's an interesting issue. The balance of, like as Shreyashree said, making sure that your redundancies are there, you're not failing, but then also making sure you don't have like a ton of wires and just a bunch of extra weight is a problem. I guess another question I had for anybody who wants to talk about it was, what are some control systems that you guys respect? Like you saw on the pod, either a competition or you're seeing a team like put together now, and you're like, that's a quality system and it's done properly. Can be Hyperloop or not even Hyperloop if you saw another system that you thought was interesting.
Well, I do have an interesting system I could talk about briefly, and it's actually the Tesla. I feel like it's the older Tesla models, but the brains was like this embedded Linux operating system, kind of like a Jetson, and they were having this issue where there was a bunch of log generation going on, and it would wear out the memory in the chip, and it would fail, and you'd have to take the car in and get it reserviced, and they'd charge you for it, and really that's just bad engineering. So what I really like to see is a PLC. That's like an industry standard, very expensive, extremely reliable device. And I think it doesn't get any better than that in terms of reliability. That's all.
A PLC sounds good, but it is so expensive.
It's true, yes.
Mm-hmm.
Mahmood, I had another question for you. You told us that you were talking to the Saudi and like UAE teams, and they're kind of doing that. Like, were they using a similar controls stack as you were, or were they like developing some a different controls system?
We have a target to build our control system, our own control system, different from others. Build our power electronics architecture for design. A controller will help us to try to apply a new concepts also. But when we changing the PLC brushless DC motor, when we're using linear induction motor, I thought we will make our own controller. We're trying to use it, but now we're using only brushless DC motor. But for further in the future, we will use linear induction motor. That's all.
Okay. I was asking more about, like, you had mentioned teams in the teams in UAE and Saudi Arabia. So I was just curious if you had talked to them about their control systems and knew anything about what they were up to.
We talked about with them about funding and support. They weren't technical members. They were business stuff. We talked with them about funding, and we're trying to apply to build a Hyperloop prototype if they are interested in that. But unfortunately, nothing complete.
I have a question, please. Hello.
Yes, we hear you.
Yeah, I have a question. How did you take into account the vacuum affecting the other electronic aspects? I read a paper that traveling in near vacuum affects it affects the electronic components.
We have an missed issue in this point, because we don't try this before. So we aim to try test our board to see what will happen. Everything is handly calculation. So we couldn't know what will happen if in the vacuum. We're also trying to measure the pressure and see what will be the effect of that on our board. That is all.
Okay. If nobody else has any questions, I was going to I'm gonna put out a poll like right now on the Zoom screen, asking if you guys feel that we should focus on innovating, like kind of evolutionary development. No, sorry, not innovating. So evolutionary development in controls where we do machine learning and kind of newer models, or should we focus more on longevity and the smaller innovations instead of large scale changes? And curious to hear what you guys say about that.
Is this in terms of the competition or in the general evolution of Hyperloop? Because those are two pretty different questions.
How about both? Start with one, go to another.
Okay.
Okay, and like while I set that up, I guess one last question I had for either you, Mahmood, or Mohammed from Helwan. is how's the discussion been going about a test track with the Transport Ministry? Do they seem very supportive of your work, or kind of indifferent, or how do they seem so far?
Muhammad Hisham told you about that.
Sorry, I haven't understood what is the question.
How have the conversations with the Transport Ministry in Egypt been so far about a test track?
The testing in Egypt?
Yeah.
Yes.
We have a contract with an organization in our country to provide us the rail to test our pod in Egypt before the competition.
Oh,
hello, are you hearing from me?
Yeah, I heard you. That's awesome. So they have a rail. They have their own rail. Sorry, I think I lost you there. I was just asking, like, so they have their own test track already, or are they going to construct one right now?
No, they didn't have a constructed track. They will build one for us, but not the full track, only IP.
All right, I think let's take a break for 10-15 minutes. Thank you so much to Mahmoud and Mohammed from Team Helman Hyperloop for talking about your control setup and helping set up this panel. I launched the polling, so if you guys want to answer the polls as we get ready for our next session, that would be great.
Thank you. Okay, thank you.
The poll question is so damn vague. I mean, there's I mean, why not both?
Oh man. Fair comment. I guess, yeah.
Half of me is like, okay, yeah, for now it's slow innovation, and half of me is like, yeah, definitely I'll be using ML. And now I'm like, what do I even do?
Okay.
Oh well.
Actually, ML and ML can be used once
Once my data is in.
Yeah, data is in, not only
Which
data
is like slightly far off.
Actual working data. Yeah, exactly. Actual working data. Not only actual working data, a lot of safety factors also. Generally, you can consider ML for optimizing.
I think the question was more about, should any of the hardware be optimized or specified for machine learning and artificial intelligence, or should we use?
Of course, that's in the cards, but that's slightly later. For now, I just need to get a pod running so that I even get data, like real life data for once. So, okay. Nice vague question.
Sorry. I guess we'll follow up with more specific ones. But yeah,
I would I would be more interested in how long will it take for the actual transportation to happen. Actually, will it be how long will it take the actual to make it running a car, in terms of running a car, like a mode of transportation? That's more of a question actually.
Exactly.
You guys tell me, you're the researchers.
Sorry?
You tell me, you're the researchers working on it.
Okay, I will be more interested in what do you say? Like how far are we along the using as a personal mode of transportation, or how far are we going to use it for a like public mode of transport, like bus in terms of that sort? So those are the questions I will be interested in.
To be honest, I think first, if we end up commercializing Hyperloop, we might end up using it for I think we should be using it for cargo first, I guess. Something like time-sensitive cargo, probably organs, for example, before using it for people. I'm really not sure how it pans out, how Hyperloop's going to pan out for people, considering the system that uses, like, there has to be a system that says that the pod opens up at 1 atmosphere, but the pod is traveling at like 0.1 or below atmospheres. And the whole airlock system completely evades me. That how is this even going to work? So that's why I'm not sure about humans. I mean, humans using humans for like transporting them.
Actually, like I was
Somehow I haven't got my head around it.
what do you say? Like I was wondering how will a person that is claustrophobic get into a pipe and travel?
So that is sad.
Imagine what you're traveling at 700 kilometers per hour, and all of a sudden this system doesn't work. Imagine that, and you're stuck in a pipe for around 10 seconds or so, and how are you going to eject from that? Imagine that situation.
Well, that's a safety systems issue.
Sorry?
Well, that's a safety issue. Like, that's a very broad safety issue. People have contemplated that for a while. Even with pneumotubes, they've contemplated putting live animals in them.
Like I would like imagine that I would what do you say, in a pipe? Okay, in a pipe you can travel. Then all of a sudden the system doesn't work, and the safety. What is the redundant safety features that can be applied? Like you're traveling in a pipe, and have we thought about like how are we going to eject from that pipe?
Probably have like gates at at some distances.
There's been some really nice blog post by Hyperloop Connected, and this is kind of like the blog page of Delft Hyperloop. They've been focusing on safety in the last couple of blog posts. I'll find the link and then post it. But yeah, there's not been much published discussions on safety from Hyperloop teams yet.
I mean, I can figure out how electrical safety will work, but then commercially, it's just a whole different picture.
Well, you don't really have like successful commercial analogs, comparison, or competitive peers for that sort of thing because they've never started. They never got off the ground for the last century because pneumotubes didn't actually ever work out as a commercial thing for live animals or humans. Yeah. Thanks for that vignette, Blake, the other day that you hyperlinked to. Yeah, I had to look at some of that other data. Like, what did the investors do? But if anyone were to participate with, for example, the United States federal government, allegedly the Department of Transportation takes safety as its #1 priority subject. So any type of work that needs to go into whatever federally gets funded for this type as transportation would have to do safety. Like that would be the general approach. Even the initial work that anyone would do is, what's the environmental safety? You have to do an environmental report. And without any type of framing for this is why it's safe to these measurements in comparison to commercial industry or what the feds are going to change policy for in terms of safety, it's going to be a tough sell. Just like get the feds on, for example, the U.S. feds on board. So like if there isn't, if teams here in the United States or really abroad, I guess like someone doesn't really step up to the plate on creating a really good framework for explaining safety and really the policies that should regulate that safety, like the feds are not going to be really in a good position to even fund anything like that. So, like, yes, the safety is a big question, but it's like if no one says it, the feds won't fund it properly. So someone's going to have to say it at some point, under the current, guise of the DOT auspices, as far as they say safety first. Whether it's lobby first, but like that's something you read in. Sorry, this is break time. I'm just sort of like winging it because like in your control systems, and this is something I came up with like Mira's comment in SpaceX getting a little persnickety about so many wires and redundancy. And I think this really touches back on what the industry standards should be for message communications and whether or not there should be some type of Hyperloop industry standard for something like a bus. Should you use serial buses or should you use something else? I mean, cutting down on the wires was a big automotive industry challenge that some automotive and other electronics companies still hold patents for, like Bosch, when they cut down on the wiring topologies. That reinforced CAN bus, amongst all things. And so you have like some of these really old, archaic in most cases, serial bus standards, just like the hardware, but also the firmware specs for any of them. Bosch still holds patent monopoly over a lot of the firmware for things just like CAN bus. Like they don't open source it. So like treating things like serial buses or as components of control system, you still have to treat them like black boxes just because as an industrial patent issue, you don't really get to have access to them. But as an industry standards issue, things like serial buses get engineered for cutting down on, the weight and other challenges of things like circuit topologies. So you can just remove, a lot of the wiring there. So, I guess my question is, if something like SpaceX is going to be setting this policy standard for startup teams using too many wires, is SpaceX really also de facto or de jure really just trying to say, hey, you should be using this type of communication infrastructure, which really kind of necessitates something serial bus like, if not CAN bus or mod bus, take your pick. Not that many, or are they really trying to say invent your own? Because maybe you come up with this other topology where CAN bus just is going to be inefficient or inferior for what you're doing. I mean, for IoT stuff, yeah, it would be inferior. Wouldn't make too much sense. I don't know. Like this is a question I guess for like everyone else. What do you think you need? In terms of control systems and like communication infrastructure, just to like figure out what hardware should you even be using. Should it be a serial bus? Does anyone want to like pick up with that? It's something.
I think the wires thing was just an optimization recommendation, I guess, that was given to the team, I believe, because this is a very common thing that I've seen in a lot of projects, that people use a lot of wires, and a lot of the time that ends up tangling, messing up on signals, random noise, or just the mech people hate it, that there's a literal bunch of wires which are not properly organized. So I think it was more of I think the wire suggestion was just like a way to say be organized and make your system sleek. And I don't really think that a company is good for just having patents on some patents on something that students want to use and completely denying them that. I think like student teams should be able to talk to Bosch or whoever holds patents and assist them to use it. Is that the case? I mean, I've seen that in quite some teams that they have
If someone really wants to break Bosch of their firmware stranglehold, I mean, great, but that's been going on for like 50 years now. It's like I don't see that as changing. Yeah.
I mean, I've seen a lot of teams that, for instance, Bosch sponsors the team, so Bosch provides them access to their tech, for example, probably some CAN tech, and that's something I've seen. So I think one way to deal with this
it's not
is
like the software doesn't
partnerships.
exist. Yeah, it's just like, are they going to give you a copyleft access or like, some public access for development of something like that? These are very strategic and also rare conversations for something like Bosch. They're not going to give up their firmware because then they lose
They
the
lose
ability
market cap.
to sell stuff. Like, so they're not going to let go of their firmware patents, even though they're doing mostly hardware. They're not going to let go of the firmware because then they can't force a hardware standard on it, and then they can't sell other tools in order to interoperate with them. For scanners, for just being able to plug in and do diagnostic work. Because like a lot of these message packets are, they're small. They're not huge. I mean, you could extend CAN bus. There's like CAN bus extended, but my opinion is I hate it. It's stupid. It doesn't really do enough structurally. It's just sort of like lipstick on a pig, I guess. Like it doesn't function the way it needs to structurally because you don't get to reorganize the packet all that much. You just get like a bigger message frame. Wow. Like that doesn't really like give you the creative opportunity of coming up with new firmware. So you could say like this microcontroller is going to work with this particular set of buses in this particular way, and this is the message structure that we are going to make sure it's fault tolerant for all of us. We can do some of that. There's some like open source firmware options for things like CAN bus, but they're pretty remedial. They're not that great. And when you look at the service vendors that build on top of that, like they're not going to give that up either. So for CAN open sorts of things, you could look at them, but people build their businesses off of them. So like there isn't that much innovation just because of industry control. Like industry itself in its own business control systems isn't going to relinquish too much of that. And so I guess like the question is, my question really was, if people are in competitions and prototyping, effectively de facto forcing hardware and firmware standards, is that also then going to create this dynamic effect where you're pushing out certain types of hardware like microcontrollers just because they're not going to integrate efficiently because you just were stuck with like some other hardware and firmware and you just don't have the interoperability opportunities for being able to develop something cheap and fast, and the students can actually access any of the software in a stable manner where it's available over a couple of years rather than just like this narrow development. I only talk about that because like I face that too, and that's why I get a little iffy about being forced into that type of development route, because auto manufacturers have already sort of dominated that, and that's where it would go. Like once you get sucked into some of these bus standards, you're just getting channeled into the automotive and like other types of heavy manufacturing industrialists that have already just like identified hardware and firmware and software for all of that, and then you're wrestling with primes at that point, prime contractor.
Speaking of which, about controls and control management for specific uses and how things would change, I would like to introduce Ryan Parker from OneLoop and Mira Welner from OneLoop, who will be talking about their pod control and power management system. Fun fact, Ryan Parker also makes some rad electric skateboards. So if you're looking to buy those, talk to him. Ryan and Mira, please tell us about what you're up to with power management.
Howdy, folks. Yes, I do make some electric skateboards, but my main focus for the last couple months has been Hyperloop. So as the head of the power team, the biggest factor that I'm aware of is the battery management and safety mainly. But first, I'd like to talk about my passion for this project. Since I was young, I always loved speed. If it had wheels and an engine, I was giving it gas. So after hearing about OneLoop, I was hooked. But with a lot of power becomes a lot of danger. So safety is the #1 priority. And satisfying SpaceX safety regulations can be very daunting. I remember the first time I opened up the SpaceX rules and regulations for the last competition, I was intimidated, to say the least. But now that I've worked on it, I think that it's not too much of a hassle. The inspiration that I used was actually Tesla's BMS that they used in their car, which actually uses a 4-wire SPI interface. Just because we were talking about that. And second, obviously, is the motor, the AC inverter. So I had some questions for you all, but I guess I could talk a little bit about my system. What do you think, Samarth? What would you prefer?
Yeah, I mean, why don't you start by asking some questions, make it interactive, and then as things happen, then discuss what you've been up to.
So I've heard a little bit about the power systems. I know people are researching LIMS and people are researching BLDC motors. And we've talked a little bit about the inverter, maybe some custom hardware or outsourcing. I want to ask, for each team, what was the most difficult safety requirement that you had to satisfy? Samarth, pick a team. Or if there's a team that wants to go,
How about you, Rhino?
Okay.
Or Reno and Strathloop.
Yeah, it's Reno actually. Yeah, what I would like, what do you say? I was reading about how pilots, traveling at higher speeds. Obviously, there is a lot of physical and the human body can only travel up to a certain I was reading about this article on how pilots are affected by G forces. How they go at Mach 1, point Mach 2 and Mach 2 and so on. So at the speed of sound. So how traveling at this speed, affects body. So I would be concerned about that. Traveling at high speeds, how will the human body be affected actually? Not to mention that I think I heard that SpaceX is going to make it circular. When circular comes into play, so the track going to be circular. When the circular comes into play, there will be a lot of G-forces again going into play, right? So how will the pod design change in that perspective as well?
Certainly. Yes, that's a very realistic concern.
Just to jump in on that as well on the Strathclyde front, I can only speak for the power systems team. It's certainly not my area of expertise, but I know one thing that Kirsty, power systems lead in our team, have been working a lot from the sort of safety side is the sort of temperature control, and it's something you mentioned at the end of your paper, I believe, Ryan. Sort of keeping the lithium-ion cells for the battery modules in a sort of optimal range, and I was wondering if you wanted to elaborate on that at all, since I've mentioned it.
Oh, sure. Yeah, lithium-ion cells are pretty finicky about their temperatures. Even like the Tesla cars, they rolled out new firmware to actually warm up the batteries before they got to charging stations, because apparently when you charge the batteries when they're cold, like really fast, it damages them. So now for space or for Hyperloop, we're not as concerned as maintaining the state of health of the batteries, since it's just a one-time competition. But the cooling system is obviously going to be a big part of the battery management system. And depending on the cells we use, I was hoping we actually use a Tesla pack, which comes with its integrated cooling system, liquid cooling, and temperature sensors, and the IC that I talked about with its SPI interface. And it's a really nice integrated circuit. It interfaces without any sort of isolation to the next pack IC. So really cool cells. Seems like a total solution, and you can buy used packs, for not too expensive. But if we were to build our own, battery pack, then, well, I've actually been installing FemFenix, which is like a partial differential equation solver package on Python, and I'm hoping to use it to calculate thermal simulations, and hopefully figure out, what kind of performance a theoretical cooling system that we were to design would, how it would perform. It's proving to be very difficult, and I might do some simpler simulations, but I certainly think that liquid cooling is the best option, and having copious quantities of temperature sensors across the pack is very important. So. Yes.
Won't liquid cooling make it heavy?
Say again?
Won't liquid cooling make my system heavier?
It may.
Because I will have to have a jar of coolant. There will be one jar of used coolant, and there will be a number of temperature sensors. And I will have to ensure that the coolant does not leak or something. And even if it leaks, it does not create shorts within the entire system.
Mm-hmm.
And overall, if the coolant is safe, I will need some set of thermal properties, some set of material properties. So how do you even go about doing that?
Well, there's it's possible to use non-conductive coolant, such as oils, mineral oil, but yeah, I mean, even with a liquid cooling system, it's like, well, most vehicles, they have a radiator. We don't have a radiator, so it's like,
We don't have that. I mean, we don't have air inside.
So it's like, I guess we just store. That's why I was thinking maybe using like a liquid immersion. So basically the cells heat up, but the heat is just transferred to the liquid mass. And then, for the entire run, the amount of heat generated is just like the mass of the liquid has enough, specific heat and mass to just absorb it and not raise too much in the temperature. So I was thinking about that, but I don't know. It's quite a difficult problem.
That's true. I mean, for now, we were considering using phase change materials because it's not like the pod is going to be running for a long time. So I was considering phase change materials. I wonder if you guys have looked into that.
Phase change materials?
Yeah. So those are little packs of this polymer that changes phase and has a decent heat capacity. So that way it changes, it goes from a solid to liquid when the batteries, so it will be like sandwiched between the cells. So whenever a cell's temperature is increased, the heat transfers off to the pouch, the PCM pouch, and the contents of that pouch, they get heated up and they convert into a liquid, and that liquid can keep a particular temperature for a long time. So it just ensures that so let's say if my PCM pouches are configured for like 45 degrees, so the liquid temperature won't rise a lot beyond 45 degrees. So that should be okay, considering the highest temperature is 55 degrees that is safely used for the cells that I'm considering for now. So have you guys looked into that? I mean,
Not at all, but that's very interesting. Thanks for bringing that to my attention.
okay.
I will probably look into that. Yeah, we're just focusing on like maybe immersion or liquid cooling. We haven't really done too much into it. My primary focus has been the inverter, but since I'm waiting on that design to be reviewed, I'm sort of focusing on thermal this week. So yeah. Does anybody else have any interesting thermal applications for their Hyperloop?
There's this thing about microfluidic, some microfluids that are being used for thermals. I didn't really understand a lot of it. It was a research paper person I know forwarded, but it was about using very small channels which have some non-conducting microfluid in them, and that cools the entire cells, the entire battery pack. It's really small, so that way that way you can cool very efficiently. But I don't know much about it. Can someone have you heard about it, and can you look it up? Have you heard about it?
No, not me.
I didn't understand that, and it was very expensive, but I love that idea a lot.
I don't know. That just sounds like what some GPU manufacturers or like other processing chip manufacturers or after-party manufacturers will use for the cooling systems. Really, it's just like how much surface area are they really clearing with any of that fluid?
Yeah, but the problem that we have is that we don't have air. Like most of these cooling systems, they ultimately cool by exposing the hot fluid to air, and air circulation somehow cools it. So that even goes for electric cars, and that goes for probably GPUs as well. Like you have to keep your GPU and your entire system well ventilated and stuff. But the problem over here is that we don't have air, so it have to be like two tanks, one with the hot fluid and one with the cool fluid.
Or pyroelectric. It could be pyroelectric, conversion. I mean, there have been some developments in that technologically, but like most pyroelectrics that are cheap and commercially available are not that efficient. They're also, like, from what I understand, difficult to install in some respects. So, I mean, like pyroelectrics don't need air. Like they're a solid, heat exchanger. I mean, if people are really going like all electric, some of their designs, and they're not going to have a lot of air access, then maybe they should think about pyroelectrics. I don't know what like non-electrical propulsion teams are going to be considering. That might be an interesting challenge.
Interesting.
Interesting.
Well, beyond the cooling system, there's also other protective features, for the SpaceX requirements, such as isolation relays on the drive battery pack and insulation monitoring device.
That's not a problem.
Yeah, initially I was like, oh no, what's an insulation monitoring device? I looked it up. I think I could develop one pretty simply.
Nah, I'm not sure, but you're going to make an IMD in-house?
Yeah, I think it'd be really easy. I actually have I have a picture of like a circuit that I think would satisfy the requirements.
I think there was this company that used to make IMDs, and those are pretty reliable. I forgot the name, as usual.
Yeah, let's see. What's the best way to show? I guess I'll just share my screen, and I'll show you. So
Got it.
this is the battery packs right here.
So your low voltage is chassis grounded, right?
Yes, and then chassis, no, so chassis is left floating, and the battery terminals are not connected to the chassis. And from each battery terminal, there's essentially a very large resistor and a phototransistor connected to the chassis. And so if either battery terminal connects to the chassis, current flows through the phototransistor and it essentially creates a logic signal, signaling that there is an insulation breach.
Oh, so what I was considering, okay, I got it. It's a Bender isometer that I was considering. I've heard of some friends use it, and it's
What is it called?
Bender makes it. It's called isometer. Hold on, I got the Reddit post for it. I'll link it here. Got it. So this company, what was that? Okay, this company makes pretty good IMD devices, and they're well tested. Thing is, I actually thought that I wasn't sure about making my own IMD because that would be kind of problematic, to be honest.
Well,
Because
I mean,
IMD is something that keeps the high voltage and low voltage separated, and even a small amount of interconnection can be very disastrous. Because my low voltage is chassis grounded.
oh, I don't think that's I don't know about that. Is that acceptable? Because I was under the impression that both battery terminals should be isolatable.
Yeah, so the battery terminals, they are the high voltage terminals. Of course, they have to be completely isolated from the rest of the system. But so my DC-DC converter will have the battery terminals as the input and the 12 volt or 15 volt, whatever I'm considering, as the output. And it will have to be enough, there will have to be enough separation resistance. And that is something the IMD, which I linked, it does. It just checks the system for separation resistance between high voltage and low voltage, grounds and highs.
Right.
I mean,
So
grounds and VCCs.
is your converter isolated?
Yep, it is.
Okay. Well, I looked at the medical standard for insulation resistance is like 50K. So if you put a 100K resistor in parallel or in series with a phototransistor, I think that would be fine, you know. But obviously, if you buy it commercially, it's probably going to be more.
It's going to be expensive, but it's definitely going to be safer. I mean, the voltage I'm working at is really high, and trust me, I myself am intimidated by it a bit. I have never worked on a system this high voltage, and yeah, I would actually prefer to use the Bender one because safety.
Well, I'm sure it'll work out great for you.
Me too. But yeah, an in-house IMD is really interesting.
Yeah, certainly. Oh, you know what? This isometer, we got one of these. Yeah, in the lab back in, I actually saw this board in our lab and I always wondered what it was.
Was it in the Formula student team?
Yeah, it's wild. Cool. Yeah. There's another thing. System redundancy is pretty big in Hyperloop. So one of the things I plan on implementing is like a backup power system. So for my system, instead of having like a 700 volt to say 12 volt DC converter, I just plan on having a separate battery pack entirely to power like our PLC and some of the control logic. But that battery pack is super critical because if it fails, you know, you're going to be out of luck, right?
I was thinking of that, but I was also thinking of that, but then I'm like, where do I have the space for this?
Right.
As the mechanical people were making the pot smaller, I almost scrapped that idea.
Do you have a secondary DC converter?
I have one DC-DC converter.
See, I would recommend two for redundancy, you know, for safety. Because if you lose that DC to DC converter, you lose your control system, right?
Yeah, I do.
Something to
But in
consider.
that case, it will be a system critical error, so my pod will just shut down.
Yeah, but will it break?
Hmm?
Does it require power to break, or if you lose control power, like, you know, you got to make
If I
sure.
lose control powers, so basically my shutdown circuit is like a 12-volt loop with different switches in that. So whenever one switch state is changed, the entire loop goes from 12 to 0, and that is when the pod considers as the error mode, and that is when the pod literally stops. So the entire propulsion system is completely isolated from the battery. That is what I've planned for now.
Sounds good.
So a DC-DC converter failure would mean that the whole 12-volt safety loop, it will go to 0 volt. So, or it will be something other than 12. It could be some random noise voltage, but definitely not 12. And that is when the pod will enter the error state. Actually, the idea of a secondary DC-DC converter is pretty good, but I'm really not sure. I mean, this one was hard enough to get by.
Yeah,
But
dude,
okay.
700 to 12-volt DC converters, that's
It's
crazy.
high.
I don't know how you got
Yeah.
But yeah, I mean, beyond that, there's sort of like the specifics of managing the battery, such as, you know, balancing algorithms and, you know, chargers. But yeah.
Analog devices makes BMS ICs. Like they have this entire range of LTC 180 something. That's like they have their entire range of BMS ICs, and I've worked on them before, and they're pretty useful. And they're actually very good. Analog LTC something. Hold on.
Is it like 6182 or something?
Yeah.
I think I saw those. Don't they require like isolation transformers?
What?
Yeah, like if you want to stack them.
Hold on. Isolation as in? I mean, definitely I will be isolating my cells. Like each cell will have a current limiter. So that is a thing.
Oh yeah, LTC 6811, right?
Yeah.
I think.
Please, what is the type of PMS you have used?
What?
What is the type of battery management system you have been using?
I'm considering an LTC for now. LTC 68 something.
I think it's this one here. I'll post the link, 6811. And then the one I'm thinking of using, which I think it's simpler to implement. Hold on here.
Yours was in the paper, right? It was some complicated name.
Yeah, I'll post it right here. This is mine. It's
yours is the TI one.
Yeah. BQ76PL536A.
Oh yeah, I do remember looking through that. Definitely.
Yeah, the TI one I like because it has an SPI protocol that's directly interfaceable with the next module in the stack. So you can stack them directly without any sort of isolation between the integrated circuits. But if you go with the LTC one, it to talk to, if you want to stack, you know, different multiple packs, then you have to introduce, you know, extra circuitry. So it adds a little more complexity, but it's totally doable.
It is complex. It is slightly complicated, yes, but I actually liked it. Yeah, so the TI one, I was not that happy with it. There were some considerations that I had with the TI one.
Yeah, the TI one doesn't have automatic balancing, so you have to supply algorithms, which kind of sucks, but I don't think it's that.
It definitely sucks.
I actually found a really good research paper that relates the cell voltage to the state of charge of a wide range of cells. It's Chinese. I forget the link. Maybe I can find it though.
Please, what is the number of batteries you have been using?
15
Was
or
this
13.
type of what?
My battery pack will be 15 stacks of 13 cells per stack.
15 stacks of what? I haven't been hearing.
It will be 15 stacks of cell, 15 stacks where one stack contains 13 cells.
Okay, okay.
So that will be approximately 712 volts.
I would like to ask another question. Have you considered any other levitation system other than LIM, or did you what was the process that you reached into LIM?
Well, I have seen a successful system that uses like 4 rotating Hallbach arrays, but it looks really complex, and I don't think it went very fast. So, no.
I mean, also One Loop used to be a cold gas propulsion team. So last year at the Hyperloop competition, we were cold gas, and that was cool. But like, I think SpaceX was not too happy about that, right? Like in terms of safety. In the end, they didn't even let us test, right?
Yes.
So,
well, but I don't think that was because of cold gas. That was for mostly our stability system was atrocious.
I thought it was structures. Like there was a hole that was like they needed an extra bearing, and it was all.
It was well. So back then we didn't have a structures team and a separate stability team. We just had a singular structures team, and they said your structures team, your stability system is bad. What's your stability team doing? They said we don't have one. We just have a structures team. So that's why we created the stability team.
I see. Yeah, it was a bummer. We put a lot of work into that pod.
I mean, hey, we did. We came in top 9th in the world in terms of test pass, so I think we did pretty well.
Yeah, not bad.
Much better than the year before. That was embarrassing.
Glad I wasn't there either.
Oh, you were happy you weren't there.
Yeah.
Regarding the earlier poll question, I meant because AI and ML, it's part of, you can include that question in the first question itself. It's like part of the innovation. Like you can include the same question in the second question is combined actually. So it's part of the innovative process actually. You can combine it together. It's kind of answers the same question though.
it was a badly formed question. My bad.
No,
it was a bit kind of vague. So Shreyashree had a good point. But
I knew it.
But yeah, like with the no, I don't. I guess that was the end of that point. Ryan, did you have where did you want to pick back up on?
Because I'm doing ML and AI actually. What I've been studying that ML and AI. So it's in the long run, everything will be turned into AI and ML in the long run. So like you can see now we are going even like for texting a message, we are going into the predictive texting. If you take up an iPhone, we are going into we don't type directly now. We just based on our previous text, it analyzes our pattern. Then we are texting. So you can see that there also ML is being used actually. So,
yeah, honestly,
and we know how badly it messes up sometimes.
Yeah, I mean, ML is gonna be big in the future, but I'm not sure it'll be so big for Hyperloop. I think it's gonna be like, deep fakes and like fake accounts on social media, but probably by the Chinese government or something. I don't know. I don't know about Hyperloop though.
I think we can use ML and AI for better modeling systems, but again, that will be a lot of computation. I'm not sure a laptop could do that. But otherwise, yeah, like I am hopeful for using this tech, especially on data that we already have, like runtime data. When processed, it can lead to a whole different level of optimization, to be really honest. So I'm kind of hopeful, but that is far.
Yeah, it's good technology, but to actually utilize it effectively, you need, a lot of data. And for most of us, we don't even have a track to test on. So it's pretty tough.
Yeah.
But no, I love ML. It's cool.
Speaking of track, how has the because this has been an issue that's come up a few times. how does the I-beam and the track that you use affect your propulsion and power management? And what have you done to, like, do you think that there's a point in which we should just change how the I-beam is set up rather than continuously changing our systems?
Mm-hmm. That's an interesting question. Unfortunately, our propulsion team leads aren't here, but they are developing like it's like a triple limb. I think they were talking about a dual limb where they have 2 limbs on both sides of the I-beam, and now they're talking about having all 3, like 2 on the sides and like 1 on top.
That is a lot of current.
Oh yeah, yeah. No, I mean, we're trying to go fast. I mean, that'll really grip that I-beam, I think. So I don't think it's too bad of an idea, you know. If we can supply the power, that is.
Yeah, that seems to be a thing. I mean, that's going to be a lot of current, and probably you'll end up using a 700-volt system as well.
Yeah, maybe. Hopefully, I'm honestly trying to go for like 200 to 300 volt system.
Why is that?
Because that would put us at like, I don't know, 600 to 800 amps, and that's like peak current draw, which is doable. So.
Okay. Fair.
Hi, I'm Beverly. I'm from the UCI Power Systems, and I just had a question about battery cell simulation, specifically with like larger cells. So if you guys have simulated them before, what programs have been most helpful?
Simulink.
Python. Literally, all the simulations I do, I don't really like ANSYS. I think the software is super hard to work with. It has a super steep learning curve.
Oh, really?
So all the simulations that I do are literally either in MATLAB or in Python, and they're sort of iterative, where I define time steps and I define, cell starting conditions, and sort of do a constant current, constant voltage depending on cell equivalent series resistance, and yeah, I have the sort of basic charging script down. I tasked one of my team members to develop like an algorithm to detect outliers and to balance this, and they haven't really done that, but I'm hoping he does it soon. I need a balancing algorithm for this IC, but yeah, just Python really.
Python, all right.
I want to ask.
I have a question regarding Python. What all package what all package do you use in Python for this?
I just use NumPy.
NumPy and SciPy are going to be pretty useful for this.
I'm sorry?
NumPy and SciPy probably.
Yeah, sure.
Like the simulations are okay.
I've just used MATLAB.
I have a question about battery simulation also. What is your target from battery simulation? To know system state of charge or charging, or
Hope that my battery doesn't blow up, for one.
Yeah, so it's to develop an algorithm to balance the cells effectively. So one of the things I've found, and it really depends on the cell chemistry, but one of the things I've found is that when the cells are charging and they're like half full, they have like a relatively low or medium state of charge, their voltage differential is very low, but getting into the 90 to 100% charge state of charge range is where the variation in voltage really starts to occur, and you really get to see the state of charge difference, and that's where the balancing occurs, is near the 90 to 100% state of charge.
Yes, I worked with a lookup table approach, or take the battery data.
So you can't use a lookup table, but I found a research paper. It was a Chinese paper that actually relates the open cell voltage to the state of charge for a variety of cell chemistries, and then that way you can actually use this parametrized formula, and I'm sure you could implement it in an embedded system.
Could you share it with us?
I'm sorry?
Could you share it with us, please?
I would. I literally don't remember. Like, I literally just Googled like open cell voltage, state of charge, research paper, lithium ion. I'm sure you'll find it. It's a Chinese paper. I'm sorry I don't have the link.
Never
But
mind. Never mind.
basically I found a formula, that relates state of charge to open cell voltage, and that's how
Yeah, I know formula. State of charge equal integration of
so
current.
that's how I plan on developing the algorithms for balancing the cells. But
Yes.
I want to go over a certain technique that you can use to actually initially balance all your cells. So let's say you buy all your batteries and they're these big cells, maybe prismatic lithium ions, whatever. If you want to balance them all, you just connect them all in parallel if you can, put them all in parallel, and then just charge them all to their nominal voltage. And maybe over a day or two, that should really balance them all out. And then you can take the cells and arrange them.
Yes. I'm working on another approach to make a lookup table of battery data and charging and discharging current based on current RPM load.
Mm-hmm.
This is my approach to know the state of charge. But I'm looking for another approach if there is another approach that available and make real data, real simulation or nearly real. So I will search for your paper. Thank you.
Okay.
I think I found it. It's is it the one that I sent in the chat, Ryan?
Hold on, I'm looking at it. How do I download it? Says I have to buy it. I don't think this is it.
Oh, it was open?
Yeah, it was free. Are you kidding? I'm not gonna pay for a research paper.
No, I mean on campus, right? Like you could probably.
No,
Anyways,
I was off campus. I just was Googling. It's a Chinese research paper, but it's in English. But it's, the authors are, I guess Chinese. I don't know. My point is, I found a formula for relating the cell voltage to the state of charge, and it's very nonlinear. But it's not a requirement, but it certainly helps a little bit. What else is there?
Yes, it's also my Simulink model also based on open circuit voltage to make a balance.
Also, adding on to the resources, MATLAB actually has a resource page created by one of their staff members there, and they also follow similar circuits to the one listed by the Chinese author, actually. And he actually created some sample models that you could follow on MATLAB. So I just put the link in the chat if anyone wants to see it.
Yeah, that's what I used. I mean, I checked out the documentation and I found it. So it's actually pretty accurate as compared to real world data.
Nice. This looks great.
Yeah, and he also has like some videos on YouTube actually explaining his paper and his work like step by step. So it's super neat.
You have a link to the paper?
I'll give me a second.
No problem. But yeah, I mean, I'm sure this is good stuff. It looks like, yeah, he's talking about 18650 specifically. That's very detailed.
I got institute access just in case someone needs it.
Yeah, typically you can even send the authors of the paper, an email. Just be like,
Yeah,
hey.
and they give it to you for free.
Yeah.
Yeah, but institute access is also pretty good.
Mm-hmm. Oh, it's great. I'm a total fan of getting as much as I can free. I don't even have MATLAB. I use Octave.
Our institute provided us with MATLAB licenses, so it was fine.
I know.
I didn't have to worry about it.
Yeah. But once you
Octave
leave
is pretty
school,
cool.
then you're going to be like, oh man, MATLAB's expensive. Better use Octave. And then I'm already here, you know what I'm saying? So I'm just
Or
preparing.
just use your student ID, or there's this thing called torrent.
No, once you leave, once you graduate, what are you going to do?
Torrent.
Yes, please say that publicly on Facebook Live. Thank you.
Oh no!
But
But yeah, Octave is pretty good. Yay, FOSS. MATLAB is expensive, guys. Use Octave.
no, MATLAB is like what we should all aspire to be like serious, like as in when we leave school and do our Hyperloop development. I was reading about how they've not raised a single dollar in funding ever from anybody, and they're like a multi-billion-dollar business. Like, props to them. But also they rip off students, so I don't know.
That's crazy.
Well, I don't know. I'm especially a fan of MATLAB documentation. It is just so beautiful. Well, I've learned so many concepts because I saw them first in the MATLAB documentation and was like, oh no, I should have known this. So they actually deserve it.
I dropped the link to the paper in the chat just in case anybody wants it.
Nice, thanks.
I had a question actually for Shreyashree. So your Hyperloop pod, I think I found your Hyperloop pod on the internet in terms of a pod that's very similar. Here, I'll show you a picture of it. Yeah, so the Porsche Taycan has a 800-volt battery. So I was just wondering if you looked at electric vehicles. I know that like people have compared TU Munich's pod and their power system to like electric cars before. I was wondering if you or anybody else has looked at like trying to work with electric
I was in my
vehicle
Formula student team last year. So
so you already,
yeah. So I was in the uni Formula student team last year in my second year, and like last year, sorry, god damn it. And it was an electric car, and yeah, I was in high voltage electricals. So yeah, I have looked into electric cars, but the one major advantage that they have is that they're not working in vacuum. The major thing I'm worried about a bit is vacuum ratings for whatever I'm using. So pouch cells, they probably puff up in vacuums from what I've heard of because of pressure differences, for instance. So my major safety concern, when I'm comparing with a car, everything is good, everything's fine, till the air pressure comes into the picture. So that's the one thing that I'm worried about. And yeah, I have analyzed the systems. They're pretty good. They're damn good. Did I answer your question?
Yeah, you answered my question perfectly fine. I was just wondering,
Cool.
like, Ryan, like what you've done, because I know Ryan, you built some other electric motor things before, and yeah, what are your take on the vacuum problem?
The vacuum problem being having battery cells in a vacuum that are untested. Well, I really like 18650 cells. Put them in skateboards, cars, vapes, whatever you want. Hell, you can put them in space, as we see from the Tesla that is currently in orbit, you know? So when people ask, can the battery go into space? I just say, look at the Tesla in space. It looks fine to me.
Wait till you see a pouch cell actually blow up in vacuum. It looks like a goddamn balloon.
Wow.
I mean, pouch cells, I probably saw some video about, my prof told me about it. He just wanted to vacuum test it, and he just dumped a pouch cell in a vacuum chamber and started reducing the pressure, and it just, it inflated.
I guess that kind of makes sense. Maybe there's some kind of liquid electrolyte in there.
Yeah.
It'll also inflate if you remove the protection circuitry and hook it up to the power line.
That's a different inflation we don't talk about.
Anyway, I posted the Chinese paper about open circuit voltage and state of charge, so check it out. That was pretty helpful when I was building my simulation. But yeah, pretty much it's just like an iterative simulation where I create a multi-dimensional array and then iterate time and then add charge based on the charging current. Sort of like a loop, calculate charging current, calculate state of charge increase, calculate open circuit voltage. And then it does that for until the cells are reaching their voltage that they're nominal, and then it plots the output. And it looks pretty cool. Now all it's left to do is to figure out an algorithm to balance it that you can implement on a microcontroller. So.
All right, this is Sam. I have a question. This is Sam from Cooper Union.
Howdy.
Hi. So you mentioned that your team was experimenting with linear induction motors.
Oh yeah, big time.
Yeah. So my team hasn't really looked at that yet, but I was wondering, and to everyone in general, what are the main challenges in developing a limb, especially because you have to. It seems like you really have to design it from scratch.
Yes, that's sort of my approach, and it was challenging to say the least. Definitely one of the most challenging projects I have attempted. Now, I want to tell you that the control system math that I developed is completely 100% correct and is going to work, and that the inverter design I built is 100% bulletproof. But to be honest, I haven't tested either of them, but I can tell you that in my first inverter design that did work, the biggest challenge was understanding exactly how the limb works and how the inverter generates current that runs the limb. And that's where my propulsion team really helped me out. And Aaron, he showed me that when you take an induction motor and you unroll it to a flat sort of piece, technically one of the coils is actually flipped upside down, because when you unrolled it, it was upside down, and you unrolled it and changed its orientation. So the bottom line is, if you have like a mini limb with 3 phase coils, and the nominal direction of current is say clockwise, then the first coil is going to be clockwise. You're going to have to take the middle coil and flip it so that the nominal current is in the opposite direction as the other two. And just like a 3-phase motor, you just have to flip one of those coils and it'll operate just like you want it. But if you don't flip the coil, then the magnetic fields will actually cancel out. So yeah, and we had a variable frequency drive at that point, and that's sort of how propulsion figured this out, I think, is they had a sort of inverter, and they just wound a bunch of stuff on some iron and sort of played with it, and they showed me that, and I played with it, and that's sort of how I initially learned, oh, these coils, one of them's flipped, and the magnetic fields created from all of them actually add to create like a large sinusoid as you traverse, the electromagnet, and then that sinusoid is modulated in time, so it's like sine like lambda x minus omega t, and where x is the direction of travel along the limb, and then t is like time, So if you just imagine that function, that's sort of how the magnetic field looks like that's generated. But it's not perfect like that, because the coils obviously aren't perfectly sinusoidal fields, but sort of like that. Actually, I have a really cool simulation I could show you, because I modeled it using MATLAB.
Yeah, that'd be awesome. Thank you.
I would also say, oh wait, never mind, you have that up now.
So you can't really see the coils. I didn't model the coils, but you see there's like a rectangle here, and then there's a rectangle here. And those are the 2 overlaps. So the coil is like, this is one coil, this is another coil, and then there's another coil right here. And those 3 all overlap by 50%. And so the middle coil is flipped. So the currents running through the coils are like essentially sine x plus 4 pi over 3, and sine x minus 4 pi over 3 or something like that. You know, 3 phases, and then you just negate one phase to like you're flipping the coil. And this was all calculated using the Biot-Savart equations. It doesn't take into account the steel core, which has a you know, it magnifies the field with its permeability, but it's sort of like just multiplying by a constant, so it's not too big a deal.
I would also say another issue we've been facing is linear induction motors have end effects, which they create the magnetic field that you want, and then they also create another magnetic field towards the end of it, and it's problematic because it can interfere with other systems. So we have had some success calculating, you know, what it's going to look like and how to make sure that we don't put, you know, say our PLC right where the magnetic field is going to be, and our PLC gets completely destroyed. That's another interesting issue that's fairly unique to linear induction motors.
If you don't quite understand what's going on in this video, the red is a positive vector, is the positive field, and blue is like a negative field, and then the intensity is the magnitude. So hopefully that helps. But essentially, the magnetic field component going out of the limb, that magnitude and direction changes sinusoidally with time and location. That's how that works. And then I think this was, I think, our battery simulation output. Just so it, on initialization, it gives each cell a sort of random charge to simulate getting a bunch of cells that aren't quite all balanced. And now the randomness is pretty small because I'm assuming that I've attached all of them in parallel and sort of got them all balanced. But if not, then you can increase the randomness even more. But basically, once you get around here, you know, you'll be able to tell, okay, this guy is sort of an outlier, got to, you know, shunt some current out of these guys. And so, you know, it takes parameters such as cell size and number of cells, etc., and shunt current, which is essentially like, you know, you have a balancing circuitry that shunts current from each cell through a resistor. And so you can say, okay, use this amount of shunt current, and that's how much it'll discharge the cell. And so like the next step in the code would be to develop that balancing algorithm. And it should allow me, the most important data I expect to get out of this is how much shunt current I need for the size of cell and the amount of variation in the cells, which I don't expect to be more than 5%. And that should allow me to design the balancing circuitry by just simply dividing the cell voltage and you know, taking the shunt current and the cell voltage and finding the shunt resistor that I need to balance the cells properly during charging.
It's very interesting that you used MATLAB for. Oh, can you hear me?
Yeah, I hear you. What's up?
Yeah, no, I was saying it was very interesting you were able to use MATLAB for all your simulations.
Yeah, it was a lot of fun, and I remember I learned Biot-Savart in like sophomore year, so it was kind of fun to apply that. Never thought I'd actually use it, but it made a really nice graphic, kind of really informative about how this motor system works. And you know, Python is just so versatile, you know.
Yeah. So did you start with the simulation, or sorry for all the questions, but or did you start experimentally with a smaller, a shorter version of the linear induction motor? Because I'm not sure, maybe the end effects.
Right. So I did start with a small test limb, and I'm not sure if I have pictures. Mira, do you think you can find a picture? But yeah, I actually started with a small limb setup with three coils, one for each phase, and yeah, and then I sort of learned how it works a little bit from there, and then I sort of did my simulations. Yeah.
Awesome. Thank you.
That's really cool.
Thank you.
Sam and Alex, what's your plan so far for Cooper Union's power management?
Yeah, I don't know if Alex is here now. He's in California, so a bit of a time difference. I think he's also on a flight, so maybe not in California anymore. But yeah, I mean, we're really starting up again, kind of from scratch this year. But so yeah, we haven't looked so much at the power system yet. Mostly so far we've looked at eddy braking over the summer. But yeah, I mean, we were planning on using last year lithium-ion batteries, and I don't remember the exact configuration that we used, but I can pull up our final report. Yeah, our main issue is actually the power system. In our first year starting up, we found that people who weren't really familiar with designing things with high voltage, high current, were messing around with the batteries, and it kind of created a bit of an unsafe environment. So that was actually our main challenge with power, was how to just delegate it so that all the safety requirements are being met. There were multiple qualified people working on it at a time. Yeah, so that's kind of our priority for power this year. I don't know if that helps very much.
No, for sure. I was just wondering what was up, like, and I really like how we're not all like the same kind of university teams here too. Like, it's pretty diverse. Cooper Union is a very different school from UC Davis, which is a very different school from IIT Bombay, which is a completely different school from Helbin University, right? Like, we all have very different setups. And I know that like one thing that at Davis we always wanted more of was power management courses. Like, they didn't teach undergrads how to like do a lot of that work. So yeah, is that a problem that like the rest of you guys have kind of run into too, or have you been able to like find all of those resources for battery management, power management, etc.?
I found resources, and one thing that I noticed was that our professors are pretty supportive. So I think I think just directly going to a prof and asking them for some help, let's say it can be some design review or something that you need, it's a good idea. Like, it was unexpected, they were unexpectedly supportive. That's something I realized.
Yeah, our main issue was really getting we have a few full-time faculty that are experienced in power electronics, but just getting them to commit, they're all very busy, so getting them to commit to advising us in that area is pretty difficult. I don't know if you guys know, but Cooper Union is a very small school.
Yeah, like Samarth said, at Davis, it's pretty slim on the power electronics front. So a lot of the development was sort of my own personal research, and I've sort of had a passion for it for a while. So yeah.
All right. Anything you want to say to like kind of close off the session, Ryan?
You guys want to see the inverter?
Say yes. It's
Yes, I
really
do.
cool.
Okay. Check it out.
Good.
That is nice.
Thanks. Yeah, that's what I've been working on for the past week or so. It took like 60 hours, but I got it done in like 2 weeks. Yeah, I got
That
a
is
nice,
damn nice.
got a nice engineering team looking at it. So hopefully they like it and I don't have too many changes. I'm excited to make it. It's all I've been thinking about, you know. But anyway, I suppose I'll close off. Thanks a lot for having me lead this panel. It's been really nice talking to you all. I feel like we all shared a lot and learned a lot. And I hope to see you at a competition someday.
Awesome. Thanks a lot, Ryan and Team One Loop. And yeah, we're going to have a last 15-minute break, and then it's off to HyperExcite to talk more about breaking and structures. For anybody who's here still during the break, just a quick question. What do you all think about open source work in Hyperloop? Do you think it's something that would make sense, or do you think it's just such a competitive field that like it wouldn't make sense because teams would just be at each other's throats, copying each other?
I think as of now, when most student teams are focused on some form of competition or another, it would be unfeasible. Perhaps in the future, I know in the US, there's not really any chance that we could actually get funded by the government. If we were funded by the government, we would totally change our entire team model into building. Oh, there are other Jews in the sorry. Sorry, just a second, housemate.
That's a big if. My ears perked up. Anyone else?
All right, sorry, I'm back. There's a Jewish holiday coming up where you're supposed to blow this horn, and I heard somebody else in the apartment complex blowing the same one, so I had to blow mine. Anyways, I guess my thought, yeah. So that, my thought is when it's competition centric, I don't think we can do open source right now.
I think I'd probably have to second that. Mostly, I think while there's competitions going on, I don't think it's particularly feasible to have sort of teams fully openly collaborating, because it would kind of destroy the sort of value of competition. But I think there could potentially be space for some kind of open sourcing within sort of Hyperloop and within student Hyperloops teams, whether that's sort of previous year's designs or small snippets of information. I think even having conferences like this is a sort of subtle form of open source, if you like, where we're sharing information. I think, I don't think we could have it fully open, but I don't think we should have it fully closed either, if that makes sense, Samarth.
Yeah, I agree with Sam. Having some sort of open forum such as this, is really helpful for teams. And I think maybe even going into the future, it might be an idea for us to set up some sort of some sort of Facebook group or something. Because I know a lot of the Formula student teams normally have quite large Facebook groups with normally thousands of members and tens of teams and stuff, and they're always on that, asking questions, giving each other help with things.
I would like to add to that what I was saying, that it's like a 50-50 take on that actually, because it develops, if it's an open source, there will be similarities in the project, and if it's a closed closed network and within the teams and all, there will be more. I think there will be more in creativity going on, because they will be bound to go for another option. Like for example, how can I explain this? One research goes into that, and you kind of deviate into a different direction, but another team goes and made it successful using the other technology. So it's kind of a 50-50 take, I would say, if it's open source. You can gain from others' developments as well, but it limits your, I think it limits your thinking as well as it's right. It limits your thinking to do something genuine and creative when you take on that actually.
Yeah, I don't know. I think that's what's so interesting about Hyperloop. Is it's a student competition that's set up for no open sourcing and kind of direct competition, right? And I think definitely earlier in my career in Hyperloop, when I was business director at OneLoop, I was pretty competitive. I don't think I really talked to any other teams. I think locally there were a couple of teams that wanted to work with us, and I don't think I even talked to them, because I was like, I don't want to communicate and give any ideas. But I think now, I mean, hindsight is 2020, right? But now I just see a lot of people have the same problems, right? A lot of the same, and it just feels like some of the basic problems that we all have, we're all just facing again and again from the beginning, and we're not making any really tremendous progress, because everybody's just going and facing the same problem again from the beginning, rather than helping each other to solve the basic problems, and then really competing on the merits of strong innovation. But yeah, I hope that more events like this happen, and I hope SpaceX realizes that too, because it's in Formula, right? In the Formula team and the Formula competition, you can have a closed source team because cars are ubiquitous, right? Electric cars too are becoming more ubiquitous. There are a lot of electric car models in the market you can buy and use, and there are set protocols for a lot of things in the automotive world already, right? In the Hyperloop space though, everything is new, right? So you can't exactly if you're starting something from scratch, and everyone's starting from scratch in everything, right? And you're building a whole industry, it's going to be really hard to really move if there's those barriers between teams. And that's why you also see like the other interesting thing about Hyperloop is the number of like partnerships and mergers, like whether it's Ireloop in Ireland, right, which is like I think 5 universities, right, like 5 or 6 universities that have like come together to work on that, or Midwest Hyperloop, right, which is the combination of the 3 Hyperloop teams in the Midwest. It's interesting to see like how they're like they're combining forces, and they're saying it's better if we just combine forces and go to the competition. So I don't know. And yeah, sorry if the symposium is grounds for anyone to like come in and see what you guys are up to. So if Delft Hyperloop somehow comes up with a system that looks exactly like OneLoop's, you know where they heard it from.
Sorry, not sorry. I mean, like, you could take the plagiarism accusation as seriously as you want to. That's the whole point of a publication, is that you can't take that seriously. But no, like, Samarth, I want to follow up on your other question. Like, if there was some, infrastructure resource or a set of patents that, any of the teams here, stakeholders think may be prudent if it were made, a public resource or something. Like, I don't know, the feds cracked down during antitrust on some large auto manufacturer, and they open up something for a serial bus, or it's a safety standard, or it's like a national resource, some type of federated, some type of large systemic resource for supporting something, right? Does anyone have any impression of about what should be open source then? If someone were to make that available, like someone were to wave a magic wand and say, like, this thing will be paid for. Does anyone have any opinion on what that might be? Other than the track. Other than the track.
I'm sorry, Kirk. It was just a little hard to hear you. But if the question was, other than the track, what other kind of research could be paid for and subsidized to be developed and spun off? Is that the question?
Well, no. I mean, it was just like, if something were to be non-competitive and public and open source as a resource, a patent or a set of equations, or some type of infrastructure, like this wireless or electromagnetic bandwidth is going to be just for Hyperloop or something along these lines, because everyone's running into this problem. So maybe there should be industry standardization, but also, well, maybe not so much copy left other than general user license, for something. Have any of the teams or any of these stakeholders, thought about what maybe that looks like, other than maybe like it could be a MATLAB subscription. I don't know. Like, does anyone have some, better informed opinions on what that might look like? Like battery thermal measurement system.
My 2 cents. Sorry if I'm just speaking on behalf of people, but in Europe, you have Delft Hyperloop at least publishing more reports publicly. Of course, all the students at Delft Hyperloop can work on this like pretty much full time. You also have there was a group called Eurotube, which was making concrete tube sections for vacuum transportation, and they were created as a foundation, actually, a nonprofit. But yeah, I don't know if I don't know. Those are the two ideas, and then also Virgin Hyperloop One, partners with DP World to develop the cargo pod. They're also Virgin Hyperloop is partnering with Spirit Aero Systems to build the actual pods themselves. But I don't know if that answers your question. I just want to give those two ideas.
Well, no, I guess at the start, I was just sort of asking, like, given all the other teams so far here have expressed some concern about things being too open source, it's, well, if any of them have a consensus on what would be open sourced differently than is right now, would anyone want to change any of that and say, like, appeal to some regulatory agency and say, hey, we would like this one thing, turn from closed source to open source, or maybe the other way around. I don't advocate the other way around.
And I think we'll have a better answer about that after this last panel.
Yeah.
So this last panel, the last but certainly not least, is going to be HyperExcite. They're going to be running a panel on the breaking and structures. So yeah, HyperExcite team, if you guys want to talk a little bit about what you guys did, what questions you have for other people, that would be awesome.
Okay, hi guys. My name is Mahek. I'm the project manager for HyperExcite. Myron, Nathan, Lana.
Yeah, my name is Myron. I'm the chief engineer for HyperExcite.
My name is Nathan. I am the systems engineer for HyperExcite.
And my name is Lana. I am the braking subsystem lead.
My name is Karan. I'm the piping and cooling engineer, lead piping and cooling engineer at HyperExcite.
Yeah. Okay, so let's get started. So a little bit about us, and we kind of briefly mentioned this yesterday as well. So our current goals as of now is to manufacture, test, and iterate a pod design that we currently have. And the plan is to have this manufactured in the next couple of months with limited lab access. So we're still trying to figure that out. But in the end, our future goal for our team is to design a full-scale pod with the approach of a magnetic levitation system, eddy current braking system, and LIM propulsion system. Do you guys have anything to add to that?
I mean, I guess in terms of, because I mean, I'm sure you guys have read our paper where there is a lot of consideration between pod 4 and our current pod 5, on whether we should keep our magnetic braking system or we should move over to a friction braking system. And I feel like a lot of considerations were taken, especially on the kind of like weight saving and like pricing side, which, I mean, it's a little sad that we have to consider more about like how much things will cost rather than kind of innovation. But it was important to us that we at least be able to get a kind of like physical idea of how the pod would work, rather than like kind of going immediately to a full-scale pod and then kind of reaching this consensus where we're like, oh, maybe we'll never see this actualized in like anytime soon for our team. Especially like we're undergrads, it's an undergraduate team. We're an undergraduate team. We only have so much time, and we can't work on this 100% of the time. So that's sort of why we took this transition to a friction braking system rather than staying with the magnetic braking system, because it was like we wanted to get a sense of like, okay, if we were to actually run our pod, here are the concerns in this simpler system, and then we can then take that knowledge and upscale it when we are then trying to push the envelope and being like, okay, so we know on a small scale pod, here are the things that popped up. Now we can take that and apply it to a bigger scale pod. Yeah, that's kind of all I had to say on that slide.
That's a good method.
Yeah.
Okay. Okay, so I guess the first thing that we wanted to start with was the ideation and conceptualization. And we kind of wanted to talk to you all about the scope of your projects and where you guys see your projects. Because for us, one of the biggest things that we... Okay, so one of the biggest things that we see or we consider is feasibility and manufacturability. Because as a senior design project, we're kind of required to have like a final design or have a manufactured product at the end of the school year, every school year. So that's kind of something that we have to take into consideration. But we wanted to talk to you all and see, well, how do you guys see the scope of your projects, and what design factors do you take into consideration when starting off your pod design?
I think that's a really good question, because finding a place to start on a project like this can be almost as hard as the whole project. So for me, since as part of the power system, you know, again, like you said, I started small and I developed like a test system, you know, proof of concept. And now I'm sort of expanding on that. So I don't know. I think that applies.
Yeah, definitely. What about all the other schools? Okay. Is there anything else that we wanted to add?
I mean, I feel like, again, the kind of scope of how you consider what the goal of your project is like, does inform what design decisions you end up making. So so like for example, with our pod, like we're doing a downscaled pod, so like the decisions that we make are in consideration with that. But I feel like listening to the other teams talk, it's really interesting to kind of hear that like, I don't know how to explain it, but it seems like your guys' scopes are a lot bigger than ours that we're planning in these like next couple months, where like, I don't know, I kind of just wanted to hear from the rest of the teams where it's like where do you see your research kind of going? Like, when do you plan on like having a pod and being able to test it? And then like, we talked a little about ML concepts and like being able to test it, get that data, and then like maybe making out and like actually developing a model.
Yeah, for Strathloop, I think I definitely we definitely mirror that sort of view of downscaling or simplifying the design this year. I think and focusing on the sort of cost effectiveness. It was one of the parts that I really enjoyed about your presentation yesterday, discussing the sort of cost effectiveness of the two braking system designs. And yeah, that really is our big focus this year, is to sort of focus on the vehicle side of things, which is maybe something that we've not done particularly well in the past, and is, from what I understand of the SpaceX regulations, a massive part of the competition in terms of proving your safety and your functionality of your vehicle before you kind of get to test your sort of high performance systems. So I hope that answers your question and gives you a bit of scope into what we're up to.
Yeah, actually, that like, thank you for talking. I think when I went to SpaceX, it was definitely like, you can't actually run the pod if they don't believe your structure will withstand the forces. It's because like when you go through, you have to have a full like safety document. You have to have like a full safety rundown with SpaceX. You spend that week testing. So it's like you have to have this validation and testing before you even be able to run in SpaceX eyes. So I feel like we learned a lot when we went to the competition last year, and we saw what SpaceX said to us about like our structures, and we were like, okay, obviously like some stuff is working and some stuff was not. We need to take a step back and worry more about like, are we meeting all these requirements? Are we for sure going to are we making sure that the force displacements are going in the right direction, or are we just sort of like making a bunch of bending moments and like creating a bunch of stress on the structure that are completely unneeded and could have been designed out? So that was a big thing that braking specifically took into consideration in our paper, where we were like, yeah, the braking force causes since we're physically braking onto the I-beam, the braking force will cause a bending moment in around the braking system. So if for example it was just an actuator with a brake pad on it, like that actuator rod would just snap off. So that's like why we added so much structure behind the actuator system, the actuator and the brake pad system itself, to kind of displace that force and mitigate it through the entire structure, rather than just focusing, like concentrating in that system and causing undue stresses.
Yeah, absolutely. I think it's a really important part of the process. I think it's still one of the big challenges for Hyperloop. You know, of course, we have our sort of high performance systems, your linear induction motors and your levitation systems, but it still fundamentally has to work as a vehicle. And I think that is something that we have also, in the past couple of years that we've been designing, sort of overlooked to a certain extent. Yeah, so I definitely second that point.
Mm-hmm.
Yeah, we also kind of wanted to know a little bit about what all the different teams are doing in terms of like braking our structures specifically, because that's kind of something that we haven't talked about today yet. And so does anyone have any insight into how their team, or what their team takes into consideration when designing their braking or structures?
OneLoop has been considering using the linear induction motor to brake as well.
Okay, cool, yeah. What about IITB?
We were considering this magnetic braking system, which used permanent magnets, or which used a combination of permanent and electromagnets. It was and LIM. So we have like 2 layers of braking systems, just in case one of them doesn't work. I'm not sure if the mech lead is here. The mech person is here. I am not that proficient when it comes to the braking system for now.
Oh, got it.
Yeah.
No worries.
Okay,
Yeah.
hi, I'm Lalit. I'm the mech lead of Hyperloop ITV. So yeah, we initially considered this magnetic braking system, and then the pod would be decelerated using this magnetic brakes in the initial phase, from top speed to some 5 meters per second or so, and then the friction brakes would be activated. That was our initial design, and then now we are going on to the regenerative braking side, in which we are trying to use different combinations of electrodynamic wheels to get that.
So I'm not sure if I 100% understand your system. So is it like, because you're saying regenerative braking, so is it like electromagnetic braking or?
No, it's not an electromagnetic braking. So there is a wheel on which I'm attaching magnets around the circumference, and then when I take it closer to the I-beam, there is some because of forces would be induced on that, and the wheel would rotate, and this rotation would be transferred into the motor.
Okay.
Yeah, Cooper Union's braking system so far, we're focused on eddy current braking with permanent magnets. Just because with coils, there's a lot of current required, and we haven't looked into linear induction motors yet, which would be seems like it would be the main use of coils for braking. Right. I mean, the other advantage of permanent magnet braking is you're not using power. Yeah, I mean, you're only using power for stability in that case to hold the permanent magnets close to the track. But we investigated kind of different arrays that you could use to to strengthen the magnetic field, so you get the most out of the mass that you're using.
Yeah, actually, I'm kind of interested in that, just because I know, like Hallback arrays are kind of the norm, just because they're the most well known. But have you guys found anything else that also looks promising?
Yeah. So going back to the basic alternating arrays, one very popular approach is to use a steel backing. So I think that's still not as effective as a Hallback array. But that's one approach. You can also use high permeability material in between the magnets. So there's a bunch of research papers that talk about different arrays and how to model them.
Oh, yeah. Actually, I've never heard of I've never heard of using high permeability in your magnetic arrays, but
Yeah, that's pretty smart.
yeah, I guess that's a good way to kind of upscale and downscale your magnetic force. Also, in terms of electromagnetic braking, I know that the team has considered it before, but SpaceX actually brought up a concern about, okay, then what's your fail-safe if the power goes off? So I think the combination between using the limb and permanent magnetic braking would actually probably be best in terms of safety, because the biggest thing about your braking system is that it will always be able to brake in the case of an emergency.
You bring up a very good point. In fact, our team recently just decided that we would be using both a limb and contact friction brakes. And we just thought, well, the limb seems, I mean, the torque curve is, it's like odd symmetric. So it can provide negative, it can provide braking. So we shouldn't need any other brakes, but obviously we need a backup, for redundancy and safety. And so we don't ever plan to use our friction brakes, but they're there in the event of an emergency.
Yeah. Actually, like a concern we personally have for our friction braking system is that, so we have our pneumatic failsafe, but that like some people within our team have brought up the concern that that assumes that you always have air in your tanks. So it's like it's not a like 100% like foolproof failsafe. But I mean, do you have any other pneumatic systems on your pod, or would it just be used in the case of an emergency?
I think just in case of an emergency, we were really even fine with like braking, like we were thinking about popping off the wheels like with some charges and just grinding on the chassis, like we didn't like, if it's an emergency, like whatever stops the pod, Of course, we don't want to damage the battery component, but,
Yeah, so just like in an emergency, brake no matter what. Like it kind of like throw out the like make sure you don't damage the I-beam, or
well, that's another problem, is we didn't want to damage the I-beam, even if we had to implement or activate the emergency brakes. But yeah, that's why I think ultimately we just stuck with friction brakes in case of an emergency. That's our redundant backup, but we're going to just rely on the limb for acceleration and braking. That's what we came up with.
Yeah, I was wondering about the limb because it seems to me that one advantage of using a limb for braking is that you can change the frequency at which the limb operates to get to change the braking curve so that you don't get zero braking force at zero speed. Is that something you guys have been looking into?
Yes, so that's sort of an an unknown sort of area. I have really been focusing more on acceleration than braking, and so I found this control system, essentially this formula that'll allow us to have maximum torque. But that's only for going forward. So for going, it should be able to be applied to going reverse, but I just have to go double check, maybe do some more math or something. But yes, it will require some complex, some drive frequency calculations. But we're already doing that anyway. So yeah, it should be fine.
Cool.
Yeah, actually, in the case of using the limb for braking, I was also kind of wondering about that, because I know, like, when reading research papers about permanent magnetic braking, they're always very like they always talk about, so once you get your array and like build your system, your magnetic braking properties are set in stone. So it's like you have this set braking curve that is dependent on velocity. So it's like if there's any variability in like when you need to stop and stuff like that, it's like with a limb at least
it's like
you
constant.
could, yeah, it's constant. Like
Yeah,
no,
it's not like that at all. It's actually, there's a lot of variables. So there's the current that's actually going through the motor, and then the frequency. And I'm pretty sure just like to brake even, you can just create a static field, just create a static magnetic field with the limb. And that should be like the same as having a Hallbach or just a magnet array that you're just dragging across the track. Now, if actually reversing the direction of the magnetic field will it cause an even greater force? I don't know. Maybe not, but that's what I'm going to find out.
Okay, cool.
Yes.
Oh, sorry. Go ahead.
Yeah, I was going to say you're definitely right about the permanent magnets. Is that your braking properties are pretty much set in stone for a given magnet setup. So I think any team that uses permanent magnets is probably also exclusively for braking is probably also using friction braking at the last stages.
Yeah, I mean, I feel like in the terms of using both both a limb and permanent eddy current braking, like that could also be really interesting to use together. Just in case you do need to change your braking properties. And then you wouldn't need to worry about the kind of stresses that you would get in a friction braking system at high speeds.
I suppose there might be a scenario in which that might be helpful, yeah.
Okay, I just wanted to ask if Hewan had anything to say about their braking system. Okay. All right, so we can move on to the next topic, which is visualization, which we took it as CAD modeling and analysis of our concepts and proof of concept, basically. So we take into consideration safety, validation, material choices. Leanna and Karen, did you want to expand on that?
Yeah, so I feel like a big thing for us, especially in terms of structures and in terms of braking, is having this validation that your system, this validation through analysis that your system isn't going to break, so you know if you designed it properly and then build it and then test it. I know, like for example, SpaceX had a lot of concerns about when we came up to them with our simulations, they were telling us, well, okay, but where's your hand calculations to back up that your simulations are even in the right magnitude? How can you be sure that your simulations are correct if you have nothing to compare them to? So again, coming in this year, we took a step back and we were like, okay, we can't just throw simulations into the void and hope that they actually validate our system. We need to personally use hand calculations to validate our system, and then if your simulations back that up, then you know you were correct. Yeah, and then I guess also in terms of material choice, since with a friction braking system, you are coming into contact with the I-beam track, you have to be sure that your I-beam track isn't going to bring any, or your pod isn't going to damage the track at all. So we were looking at a lot of material properties and friction characteristics of our brake pad material, and thinking about that before we finalized our brake pad material. Yeah.
To kind of add on to that, taking material choice from a validation standpoint. So to give you guys a little bit of a background, for Pod 4, we used a carbon fiber chassis, which we manufactured ourselves. So we ran simulations and stuff on that. But when it actually came time to manufacture, we found that carbon fiber is actually really difficult to manufacture. We used 12 layers of carbon fiber, which is overkill, but it actually turned out much thicker than we expected. And it was very difficult to validate the integrity of our structure. So taking that from a validation standpoint, I know that a lot of teams are considering using carbon fiber, and it was actually one of the considerations that, for the reason that we chose to switch to an aluminum chassis. We didn't really talk about this in the paper, but we switched from a carbon fiber chassis to an aluminum chassis just for a validation standpoint and a manufacturability standpoint. So for the teams that are considering using carbon fiber for any number of reasons, how are you guys approaching your manufacturing and your validation so that, you know, the end product that you actually have is something that you can say like, hey, this actually stands up to these ANSYS simulations that we did, and we can 100% certify that, you know, these will not just end up failing.
In the terms of simulating carbon fiber as well, a big problem with our simulations for pod 4 for our carbon fiber chassis was not necessarily that our chassis ended up weaker. It was more so the material properties in terms of like structural simulations, they don't take into consideration the epoxy that actually comes with the carbon fiber. And so when we ran the sims, we were like, oh, it's fine. But then when we were manufacturing, we were like, this epoxy adds a whole bunch of volume. And now we've realized that our chassis is like incredibly thick and very, very, very strong. Like there were no worries about it breaking off, but also it's a lot heavier. So in terms of personally manufacturing your carbon fiber, there's also a lot of it's inexact in terms of your dimensions.
There's also like multiple ways you can configure carbon fiber. So, you know, you have unidirectional carbon fiber layers. You can have a kind of like a twill sort of carbon fiber. So yeah, there's, at least for us, we found that there was a lot of consideration going into carbon fiber, especially since we were manufacturing it ourselves. So for those of you kind of taking a carbon fiber route for some of your designs, like how are you going about manufacturing? Are you getting it, you know, manufactured by somebody else? Or are you guys doing it in-house? Yeah.
I think for Strathloop, I was the structures lead last year before I became team captain this year. So a lot of my stuff last year, we really looked into using composite materials quite a lot in the early phase of the year. And I think we sort of ran into quite similar problems that you're describing there, just about validating your components through ANSYS or through other means. So we also ended up going for an aluminium chassis, and would also be very curious to hear if any of the teams had sort of cracked carbon fiber in terms of a validation methodology.
Yeah, so I kind of see carbon fiber very much like how SpaceX handles welds. So, you know, they don't allow us to weld because you can't actually determine the strength of a weld because every weld is technically different. And I think from our experience, we found that carbon fiber is kind of similar in that sense. There's a lot of determining factors of how your carbon fiber layups turn out because of you know, your manufacturing process. As Leanna said, epoxy adds like layers, and if you don't have proper carbon fiber vacuuming systems, you end up with these beefy layers of carbon fiber. And so that was kind of like my question to you guys, is that just like how you would handle validating a weld, how would you validate carbon fiber that you've manufactured? I don't know. I thought a couple other teams were using carbon fiber. Maybe I'm mistaken. But yeah.
Yeah, I think I was reading in the structural paper, I believe it was One-Loop, they were considering some carbon fiber.
Right, and I know nothing about it, but that's true. They are.
Okay, cool. Okay,
Last
then.
year,
Oh yeah, go ahead.
last year we used aluminum, and it worked, but it was really heavy. So we're using carbon fiber at the moment. We the main issue we've been encountering, honestly, is rather than like a technical structural issue, just the difficulty in laying carbon fiber. That's a technically challenging thing, but we haven't really come up with any, it's not like with brakes or propulsion where we're having a very technical kind of, we're analyzing something that's not on the math isn't working out.
Yeah, actually, we also personally ran into that problem for Pod 4, especially in the terms of our chassis. That is something humongous, and like it. Obviously, for a proper carbon fiber layup, you want like vacuuming, but for example, it's incredibly hard to figure out the kind of ways to work around that. And I'm not sure if we, to be honest, 100% did. So maybe it would be good to kind of reach out to people who are more experienced in the subject, because I know that, for example, I know that previous teams also did carbon fiber layups, and they got a lot of help from someone in industry, and he helped them make like a really nice chassis that did not have the same kind of problems that we did in Pod 4.
Yeah.
Yeah,
All
I think it's a challenge. Sorry.
Go ahead.
Do you want to go? I think it's like when you're sort of going through any sort of difficult validation phase. I think no matter what component it is or what material, I think sort of having a keen eye on your safety factor that you're designing to is really important in that scenario. And it sounds like you really did that with having sort of what was, I think, quote, overkill on the layers of carbon fiber. I think that really sort of, while you don't have the knowledge of the sort of validation methodology and maybe some limitations in manufacturing as well, which is so critical with carbon fiber, as you mentioned, then really just sort of whacking up the safety factor a bit is sort of how we had gotten around some of the problems in initial design before we sort of switched to a simpler material to validate.
Yeah, I think safety is a great segue for the next thing that we wanted to talk about, which is testing and safety. So personally, for our team, some of the testing methods that we use before testing the whole pod is using a braking test rig, pneumatic testing. So just testing the pneumatic cylinders and that whole system, and then also doing open air tests. So we wanted to know a little bit about what you all do in terms of testing parts of your pod before putting the whole thing together and testing it. And if Leanna, Kern want to talk more about the braking test rig, go for it.
Yeah, so for our braking test rig, so the considerations like we kind of have to take, or that we were kind of thinking of when we were when we're looking at our braking test rig is, if you look at it, we're braking onto this aluminum rotor, which does simulate like thickness of the I-beam track, but also thinking of the differences in geometry. So there will be a lot more problems about trapping heat in the braking test rig than there would be in an actual pod setting where you're braking on the track, but you're constantly leaving that track behind. There's also were a lot of vibrational concerns because you're spinning this very large disc at incredibly high speeds, and then you're braking onto it. That's going to cause vibrations, and then that's going to be unsafe. Not even in terms of actually running the pod, in terms of running the braking test rig and you trying to test. So it's its own kind of design problem, but it's also incredibly important to be able to test your braking system and know your actual braking characteristics before it gets on the pod, and you kind of find out, oh wait, my braking is not what I expected as you're doing the full pod run.
Yeah, we also we built a braking test rig last year. Actually, I wasn't involved in that, but that definitely our next step as soon as we can get it's difficult with COVID, but as soon as we can get access to some of the labs, we'd love to do some actual braking tests. But it looks pretty similar to what you have up. Just the magnets were kind of arranged in the other dimension, pointing perpendicular to the surface of the of the aluminum wheel. But I was wondering, it looks like is that kind of rectangular block on the left your magnets?
Yes. So I wasn't the one who ran these tests or designed this test rig, but yeah, from what I remember, like that was how we tested our brakes in Pod 4.
Okay, because one issue that definitely was brought up in some of the papers we looked at was the curvature of the wheel as opposed to the track, right? Because in the track you don't the distance between the magnet and the track is constant, but when you're testing with these rigs, you have a distance which isn't an air gap which isn't constant, right?
Yeah.
You have to make sure that it seems like to get accurate results, you have to make sure that the magnetic array is short relative to the diameter of the wheel.
Okay. Yeah, I suppose it's like similar, like kind of worry about vibrations in your disc, because whenever you run a flywheel, there will be vibrations. So the ways to minimize that in order to get accurate readings is incredibly important for magnetic braking, especially.
Yeah.
Does anyone else have kind of like thought about their braking testing?
Yeah, the test rig looks a lot like the one at One Loop. Sam built it, and it's just this giant steel structure with the friction brake, and he was sort of getting into the experimenting with the magnets, but it looks really similar.
For IITB, who is using a magnetic braking system and a limb braking system, I think that's correct. Are you guys testing in like the systems together, or is one more of like a fail-safe rather than
the magnetic braking system is fail-safe.
Oh, I see.
And yeah, I had a question about this braking system. So is this designed for a straight track or a curved track? Because the difference which I see is during a curve, which is the upcoming SpaceX track. So if the power fails during a turn, the pod, so there will be something, while the pod is turning, the I-beam might not be exactly at the center of the pod. And if at that time the power fails and the friction brakes get activated, so wouldn't there be an asymmetry within that? Is it allowed?
Yeah. Actually, we haven't really considered a curved track, but in the terms of an actual Hyperloop concept, you would need to worry a lot more about those kind of concerns. I mean, I guess because I'm wondering how much you would expect the variance to be, whether you could kind of assume, or not assume, but like kind of rely more on stabilization for that kind of help, rather than like any concerns to the braking system itself.
Yeah. Okay. Okay. So if no one else,
Oh, I have one question.
yeah, go ahead.
Do you have any insight into good friction brake materials?
Yeah. So when we were choosing our friction braking material, it was a lot more based on material hardness values first, and then after that looking at the actual friction characteristics. I think, I mean, honestly, we were kind of looking at brake lining material that is sold by companies. It's rather than considering anything else. But when we were doing our initial like kind of look, it was like, okay, what are some common materials that are used in braking? How are we, and then we narrow it down with hardness characteristics, and then we kind of figure out their temperature stabilization characteristics. Since obviously in a full run, that would be a big concern. Since we're doing a smaller run, it's less of a concern for us. So we picked our brake material kind of under the consideration that we're not gonna reach incredibly high temperatures. But I think a big thing when designing is like, it's kind of hard to get brake lining material. Honestly, as like an undergraduate team, it's like, where do I even get it? We're ordering ours from McMaster, and I picked what would be the best one for us from there. It was like, it has like a high continuous braking temperature of like 470 degrees and a brake friction coefficient of 0.47, which was like, we're not considering that we're going to get over 480 degrees when we're braking. So that was fine for us. And then like, because of the tight spaces, the tight constraints that the I-beam kind of give you, the fact that we can manufacture our own brake pads rather than actually like buying brake pads from like that helped us kind of fit to our dimensional constraints of braking onto the I-beam.
Interesting. I remember I don't know, one of the leads, I think the brake leads was talking about how we would need these special brake pads from some like Formula One car racing company, because our target velocity was so high that it was gonna like melt them or something. Did you ever encounter anything like that?
Yeah, actually, we were also kind of looking at that when we were doing our initial look into brake pad material. But I don't know, the thing about kind of ordering brake pads made for cars is that they didn't really fit the dimensional constraints of braking onto the I-beam track. Like, they were way too big for us. So I guess with that, it'd be like, well, then how do I kind of get this material, because that's what you really care about. But I don't know, it's like hard to find it. But I know that I was looking into like ceramic brake pads with like lithia, because that's what's kind of used in Formula One, and that has really good like temperature characteristics at high velocity or at high temperatures, but it's also kind of wondering like how high is your velocity, because yes, for Formula One racing you do reach incredibly high temperatures, but it's also like you are braking onto a rudder, so your temperature goes up very quickly. But since we're on an I-beam track, you are leaving a lot of the heat behind. So I don't know, you may want to kind of look at it and be like, how much heat do I really retain when I'm braking? Because like when it's with these kind of braking systems, it's like, yeah, take into consideration what the literature says, but also take into consideration that they're talking about a different kind of geometry. Because like I ran into this problem as well, where I was reading this paper, and my advisor was like, well, this is the reason why this is talking about such high temperatures is because you're braking onto a cylindrical disc where your heat is trapped. But like for us, the temperature concern is less than you think. Obviously it's not arbitrary, but it may not be as big of a concern as you think it is.
Yeah, because when he told me that, I was like, really? That can't be right. You know, it was hard to picture. That makes a lot of sense.
Yeah.
Thanks.
Okay, does anyone have any other questions, comments?
Yeah, can I just ask for the teams that have like braking test rigs and are running some sort of like contact braking, like what sort of testing did you guys run, and like what values were you kind of recording and analyzing from that?
So we're redesigning our braking test rig because our original test rig was built for magnetic braking, but currently the kind of information that we want to get is like stopping time and like kind of like braking force, though I'm not 100% sure on how to set that up. It's more in the preliminary stages for us.
Okay, thanks.
What about some other teams, if they have any braking test rigs? No? Okay. We can move on then. Okay, so the takeaways from working, as we said, our team has been working on this for the past 5 years, ever since the SpaceX competition started. And so we have been weighing, especially lately, we've been weighing what it's like to work on a small scale pod versus a full scale pod, and where we see our team in the future working towards, and also keeping in mind feasibility, because that's a really big thing with the limited funding that we have. So we wanted to kind of open it up to all you guys and ask how you guys see your teams working in the future. Are these some small scale versus full scale? Is this something that you've thought of? Kind of where do you see yourselves? Yeah. Does One Loop want to talk, or?
Yeah, sure. Well, for me as the power member, team, I see building this inverter in probably the next 4 weeks, and then gathering data, analyzing should take a week or two, and then it'll be working on the full-size inverter. So like 600, 800, 1200 amps, we'll see. But you know, that's going to take like another 6 months to develop probably. But hopefully by then, you know, a lot of the coronavirus will have cleared up and the labs will be open and we'll be, you know, ready to produce our own, you know, chassis, and hopefully we'll secure some funding and we can buy all the things that we need, and, you know, we'll have our final design review and we'll build it. And hopefully there'll be the competition, and we'll be volume.
I'm not super optimistic about the competition date being this summer. I do think it will be before 2022 is kind of my estimate. Somewhere between 21 and 2022 is I think when it's going to happen, based off of we are very fortunate and we have a mole in SpaceX. Well, in the Boring Company. Our systems engineer from last year now works there. So, and he said that Musk seems to be a lot more interested right now in the Boring competition than in the Hyperloop competition. That said, he has tweeted, because I guess Twitter is how important people communicate these days. He has tweeted that he does, you know, I think you guys have seen that he does want to have a 10-kilometer test track with turns. So he's thinking about it. This is a very long-winded way of saying I'm not too worried about getting the pod fully completed by July. I sincerely hope it will be, and I think it will be based on the speed of our team. But my real hope, and Ryan, I don't think I've told you this, but I've talked about this a little bit with Luke. It would be really cool if we could get our pod completely finished by the summer, as if there was going to be a competition. And then when it's done, just test the shit out of it for like the next 5 months until we have the most perfect, like bulletproof pod you could possibly create, is my goal. So that's kind of where I see the pod going. And yes, it is still very competition centric.
Okay, yeah, definitely. We're also keeping competition in mind and looking at how we would design if there was a competition sometime in the future, and kind of looking at our timeline accordingly. But what about IITB or Hell1?
We're a new team, so I guess it's going to be some time till we actually make a pod, to be really honest.
Yeah, definitely. And are you guys, like, how are you planning to go small scale, full scale, or kind of?
So we're working on the SpaceX pod as like a long-term goal, because it's going to take some time to get that system sorted. There's going to be plenty of testing. There's going to be plenty of design iterations, etc. For now, we're working on a smaller pod, which is more open air and works on a very simple gas thruster system. So that is like a small pod that we're making, so that like we can all kind of practice on that in a way. And we actually submitted that pod to Arizona for the AZ Loop competition, and we ended up in the final round. So it was pretty okay. It was pretty well designed, and we're taking that as our first pod for now. And SpaceX just shares a SpaceX pod, which is the complete 712 volt pod. It's a slightly long-term goal for us, because we need a lot of things. There's a huge checklist that we have to manage before we actually get to making that pod.
Right, yeah, it's quite large, definitely. Yeah. What about Hell1 or Cooper Union or Strathloop?
Yeah, for Strathloop, I think the primary goal of the team is still very much focusing on competition ambitions, trying to produce our pod for next summer. Whenever the competition is going to be, I'm sure Mira can keep us all updated on when it's going to be. We also have some other stuff that kind of the time and sort of COVID or the time from COVID has allowed us to investigate some interesting scalability projects, not necessarily sort of scalable pod projects, but some stuff to do with sort of full scale Hyperloop, which we hope that we can show off to you guys next week. Yeah, so stay tuned next weekend for some more information on that.
Yeah, awesome. Cooper Union, you guys want to talk a little bit about your future? No? Okay, all right, that's cool. Okay, so we're basically at the end, and we just wanted to ask if anyone had any final questions or comments, suggestions.
Yeah, I have a question to, yeah.
Oh yeah, go ahead.
Go for it.
A question to all the teams. So, before, while you're making your first pod, what do you think are the things we need to consider before making the first thing, so to get it done?
Like your initial considerations?
No, the initial model of the pod. So how should we go about it? So basically the theoretical design and the practical implementation would be, very different. So what do you think? How should we go about it?
So for Hyperloop specifically, we took, so when we were designing, we were taking a lot of the physical considerations into account first. So things like I think the SpaceX rules and requirements is a good starting point, even if you're not planning on like designing for it, just because they bring up a lot of concerns that kind of enlighten like, oh, this is what I should kind of be thinking about. So they bring up a lot of like constraints in terms of where you can be in relation to the I-beam, what you need to think about when you're coming into contact with the I-beam, things about not damaging it, a minimum structural factory safety of 2, and things like that. Does that kind of answer your question, or?
Yeah, thank you. Anyone else?
We don't have much experience as such with building and testing our systems so far, but what I would definitely say is, like, from maybe our experience of designing over the past couple of years, is that definitely sort of designing for manufacture is so important for anything that you design in Hyperloop or even in a broader sense. I think making sure that when you're designing a system, you have in mind how you're going to source it, how you're going to build it, how you're going to test it from the get-go is really important to sort of having a successful build phase. I'm sure some more experienced teams than ourselves can potentially back up that statement.
Okay, well, it looks like we are at the conclusion of our final session for the first weekend of the Hard Tech Fun Hyperloop Symposium. Thank you so much to the different teams that had participated and submitted the work. In the midst of all of the many crises that are going on at the same time, I truly appreciate it, and we really had a great time hearing from all of you. We hope that you all had a great time as well, and you learned something from one another, and hopefully we're able to learn from this and do some awesome work in the future. If you're interested in submitting next week or coming next week, which is more going to be on the scalability of Hyperloop, we still have room. Right now it looks like it'll be Strathloop, and DGW Hyperloop from India will be there, potentially our loop. So it should be a fun time. But yeah, thanks all for watching. I'm just gonna end the live stream now.